Let's get going, why don't we? Now, I have some plans for today. Let's do a few levels first before we get to that, though. Okay. Build a circuit with delay of 6, the gate cost of 5. So this gets us the delay required. Now we just need to add more NANDs. Which this is the dumbest possible way to do that, but anyway. Alright. But here at the stack is probably where we're going to... Okay, what's the lab actually first? Like the component factory, this is not a normal level, but a tool. Okay. Uses programs to test your circuits. When the programs are run, the level checks the link components behave the way you expect. Expect keyword is used to describe what value memory address should hold next tick. Okay. So this is just a level with an extra debugger turned on. Here the first line says we expect the second linked component to hold value 4. Yeah. All linked components are checked against expectations every tick. All linked components are expected to be 0 at the start of the program, and expectations for memory components only change as you specifically change the expectations. Set input. Control the input of the computer. Okay. Oh. I've unlocked all the 16, 32, and 64-bit components you have in the sandbox. Okay, we actually have 32-bit components available. And 16-bit ones. Which could be useful for a few things. Usually even 8-bit computers use some 16-bit stuff like memory and stuff like that. Okay. That seems useful. Anyway. Now. Let's go to the stack. The product of nibbles is probably about multiplication. Okay. Each take the inputs either signal push or pop. The push, store the value on top of the stack. When it's pop, remove the value from the stack and output it. We're just implementing a stack component. Alright. And I'm willing to bet this will unlock a pre-canned stack component for us. So we're going to want a RAM chip. Okay, this is the push or don't push. That's pop or don't pop. Alright, well guess what? This is going to be quite simple. When we're popping off the stack, we do want to energize the output. And we want to energize the load. And when we're pushing... Okay. Now here's where we run into excitement. Let's check exactly how it's coming in. Each tick, the inputs either signal, okay. So we shouldn't have to worry about both coming in at once, which means we're not going to have to worry about delay and stuff like that. There we go. Okay. Now, we need a counter. Though I don't think a counter is going to be the right thing here, because we don't want to increment per tick. Or we need a manually tickable counter that can either go up or down. So we want to register. We need to feed the register into itself via an adder. Or actually between a pair of adders. Okay. Now. Wait, we don't want to negate that. We do want to have a negate there. But not for that. An 8-bit constant. And we'll set this to 1. Okay. So this is adding 1. And this is subtracting 1. We're not going to institute any logic to prevent stack over or underflows right now. I'm going to hope I can avoid that. Need an 8-bit mux. Okay. And then we want to permanently energize the load. Then if we energize this pin, it should step the counter either forward or backward depending on this pin. That is the idea anyway. Okay. And if it's not energized, it's backward. So, if we are pushing, we want to energize it forward. Popping, we don't care. Furthermore, if it's a push, we also want to energize the store. Okay, for this though, we want an OR gate. Okay. The other leg of the OR runs to the pop. If we get a push or pop, we energize the step. And then the address is that. This probably doesn't work. Yeah, we're not. Oh, I forgot to energize the actual store instruction. Okay. If we are pushing, which is this, then we also want to, here, you need to move. Make a little bit of space here. There, for pushing, we also want to energize the store. 251, 216. Pop 216 off the stack. Okay. We need to de-increment and then energize this. Oh, I know what I need to do. Or I know an easy way to do it anyway. Okay, where's that 8-bit mux again? Boom. Okay. In the case of a pop, we want to use the value that is 1 less instead of the value that's 1 more. And note, like a real computer, it doesn't zero out memory that it leaves behind. Okay. That was pretty easy. Now, note, we don't handle any overflow or underflow errors. Okay, here they want us to add push and pop instructions to the computer and when to bat. Yeah, this is multiply and divide, which I don't want to mess with if I don't have to. Yeah, anyway. Doing multiply and divide efficiently in hardware is something I would rather not mess with. Okay. Add a stack to computer and write the program that solves the level. When input is 0, you should pop the value off the stack. When input is not 0, you should push it to the stack. Okay. I am going to completely re-architect this computer now. Also, I really don't like this stack component. Let's go to the component factory and load up the stack. Oops, nope, that's not what I want to do. Okay. First of all, let's move some things around a little bit. Okay. This thing's an awful mess. Let's just move some of these pins out of the way. Deal with later. What I really need to do at this point, move this up. And we'll add a few off gates. Just square it up. Okay. Go. You get to go right here. And we'll rerun this cable. And we'll rerun that cable. Except we want it to go the other way. Okay. Now, set these labels to all go up. And I would like to insert circuitry to send over and underflow signals. They can be used to set air flags. Okay, what is the best way to do this? Well, overflow will be hit. Okay, underflow should be hit if we have gravity quality check. And then 8-bit constant. We can get rid of this. Set this to 255. It will trigger an underflow check if the one less signal. Okay, we need to add some I/O. Output 10. Output 10. Okay, this one is overflow. This one is underflow. Okay, so technically, this is not actually an underflow condition. So we need to energize this if, and only if. Here, let's move you up a little bit. Actually, let's move the whole computer up a little bit. There we go. Okay. We need to activate this if and only if we are currently in a possible underflow state, and move these down a little bit. We're currently in a possible underflow state, and we are attempting a push, or a pop, I mean. There we go. So if you receive a command to pop, in this state we would be in underflow, because this is 255. Okay, now overflow is, I think, the exact same logic. But it triggers if this wire is at 255 and we trigger a push instead of a pop. So copy this bit. You want to, or oh no, that's a separate signal. Okay, yeah. We'll put this over here to get it out of the way. Because we do have room over here and we have a dead gate we can just get rid of. Okay. This is the signal we want to check. And we are doing a pop, or push, I mean. Just grab off that. Then boom. Okay. Now, if we set the register to 255, why would you make it look just like the value when you can't actually set the value? Can I manually set the register value? No, I can't. Well, that's not very helpful. So you can't test that part. We'll assume it works. That is a terrible idea, by the way. Also, this needs to connect to that. All of these are connected one down from where they should be. Oops. Not sure how that got screwed up. Anyway, it's fixed now. Okay. We have over and underflow signals. Now, are there any conditions where these could arise in actual operation? I don't think so. Because if we're in the final cell, and we ask it to pop, this will be 254. So we should be good. I don't think we'll actually be able to use the final cell. But that's just the way things are. Because if we're in cell 254 and ask it to push, it'll report an overflow. So we're basically wasting one cell. This is one way to get to the end of the RAM. We just push zeros. Push V5s for variety. How about... Oh, let's see. And then we want... Boom. Let's see. There, you can write with hexadecimal. Anyway, let's just push zeros for a while. Technically, even if we do overflow, it will wrap around. I'd like to use the overflow signal. Okay, boom, it reports an overflow right here. Because we're asking it to push. If we don't ask it to push, we're good. Anyway. What I should do is if an over or underflow is detected, I should suppress further incrementing. I don't know. I think we'll be okay. Yeah, I think we're fine. Let's test this a little more aggressively, though. Okay, we want to push. Oops. On both push and pop on her at the same time. That's bad. Kind of don't want separate push and pop signals in a way. It would almost be safer if there was a mode and enable pins instead. You'd have mode, push or pop, and then enable or disable to actually do the action. But, I'm not gonna change it right now. Alright. Let's push 1. Push a 2. Push 3. Push 1. Push 2. Push 3. Pop 3, okay. Push a 4 instead. The basic stack operations are working perfectly fine. Now let's push a whole bunch of 1s. Hello, survey. You should be happy right now. We're into the very easily understandable stuff. A simple stack. Which I am extending from what they had me build to do over and underflow signals. Okay. Reporting an overflow right now. It should not be reporting an overflow yet. Why is it reporting an overflow? Oh, because the signal we're using is not the actual correct signal. It's a good thing we test these things. We don't want to pull that signal. We want to pull this signal. The one from the actual register. Okay. Alright, let's try that again. Every time I change something, I have to press next 255 times, roughly. We will not be able to use the last cell of memory. So that's fine and expected. We could probably do more complicated logic. Okay. After the next push, it will light the overflow. Okay. The overflow is a little too greedy, actually. Because when overflow lights, it means it's going to overflow next time. Let's pop a value. We push a 3. And the next time we ask for a push, it'll say overflow, which is correct. It could technically write that value. Like if we go ahead and push a 4 anyway, it'll do it. But then the counter wraps around. So if you ask it to pop a value, we get underflow, which is correct. And it does, you can pop that last value, but you're going to get an overflow or an underflow tag to get to it. Okay, I think we're probably okay to use this now. All right. Sure, let's do multiplication. Multiplying two 8-bit numbers gives you an 8-bit, 4-bit numbers gives you an 8-bit number. Build a circuit that does this. Okay. There are several ways to multiply. The dumbest possible one is to simply add in a loop. A much smarter way to do it is to bit shift. The problem is I know how it is done, as in I know that you can make more efficient multiply circuits by using bit shifting. I know how bit shifting works, all that fun stuff. However, I do not actually, I've never actually done it. So first of all, let's take our 4-bit numbers and let's turn them into 8-bit numbers. Because that's going to be more useful. Okay, now we have two 8-bit numbers. Now, multiplication, like addition, can work with the numbers either direction. So it doesn't matter. Not like subtraction where one is one thing and the other is the other. So, the easiest case is where we have 1 times, let's say, 2. Where the result should be 2. If we're doing simple multiplication only by powers of 2, then pure shifting will work. And we're probably going to want to start with some amount of shifting. How much do we want to shift by? Is the big question. Also, do you have this hooked up right? Yes. Okay, let's remove this for now. If it's 1, we don't want to shift at all. Right now, we don't care about the 1 bit. If it's 2, we want to shift it once. So if we do, say, 2 times 2, that should be 4. Let's just go hook up a constant to this for now. Boom. Okay. If it's times 4, then we want to shift it twice. That should give us 8, which it does. Okay. We want to shift it once more for each space farther to the left that's lit up by. Actually, I wonder if I can do this in stages. Like here, let me give you 8-bit. Okay. I want to try something here. No, I want... Damn it. There. Where's the multiplexer? Okay. Let's actually do this over here, because that'll make it more efficient. Okay. We don't care about that for now. Let's see if this even works. Because what I'm thinking is it might be possible to chain shifts. Probably not. This is just me trying to figure out if something works without actually trying to figure out if it works, if you know what I mean. Okay. Now, Okay. 1 times 15 is indeed 15, but we're not doing any shifting, so of course. 2 times 15 is indeed 30. However, let me grab another 8-bit maker. I want to be able to see what value is coming out here. 6. $15 times 6 is 90, not 120. So, this does not work. Which isn't too surprising. However, we disable this stage. We get the result out. And then if we remove this line, okay. Let me try something here. Yeah. All right. That won't work either. Okay. So this idea is completely unworkable. And it's not immediately obvious how to go from like the shifting gets us partway there. Let me think. This is where my badness at math is going to jump up and bite me in the ass. $15 times 6 is 90. $15 actually, wait. If I only shift it by 1 space for each additional. Yeah, no. Because of course not. Yeah. That was a dumb idea. Alright, we're gonna have to do at least some amount of addition in a loop. The problem is figuring out the remainder from the first shift. And we need to decide, okay, first of all, we need to decide what the magnitude of the shift should be. And then we need to decide what the remainder is. Okay. A fast 4-bit multiply. The simplest algorithm for multiplication involves repeated shift and adds, which I knew. Okay. First cycle, A is added to P if the least significant bit of B is 1. A is shifted left while B is shifted right. Okay. This process is repeated in subsequent cycles and completes when b equals 0. That's the add and loop method, basically. Single cycle multiplier. Okay, that's just chaining. Yeah. That's not a more efficient method. That's babies first. Which admittedly I probably should just do that. Yeah. Yeah, we should probably just do that. No sense getting super fancy on something I'm not good at anyway. Let's see. So, we're going to need some shifts. Shift right. Oh, wait, here. Let's turn these back into 8-bit values. I kind of want 4-bit values for this. We need to make... Okay, we can't use custom components here. I was thinking about making a custom component and calling it a nibbler that took in an 8-bit value and exported an 8-bit value with half its stuff stripped off. We'll just have to make do with this. The idea of this is that we're able to shift and discard bits as we go. I don't think we need that. If we're shifting right. Look at this again. Okay. We are going to need a register. Okay, they don't give us a register. We are not going to need a register then. We're going to have to do it in stages. Okay, thankfully we only need 4 stages to do a single cycle multiply with 4 bits. Yeah. This should be pretty simple, actually. I mean, adder. We're probably not going to need shifts at all, then. I need... Why did I only grab 1 adder? We need 4 adders. So what we want to do here is we need to do adding let's see. Okay. It looks like what they're doing here, which is kind of weird, is ORing the values together. And then adding that to the result from the previous one. Let's get this a little more neatly lined up. There we go. Be about right. Okay. Basically, individual bits from here get added into. We're going to need an 8-bit maker for every single one of these, aren't we? More than that. Okay, we're going to need to make a bunch of values over here. Okay. You are the ones place. Twos place. You are the fours place. You are the eights place. Then you take some. I think they're using ores. This is just 0. Oops. Okay, and this is the 2s. This is the 4. Over one more. No. Okay. Now, we shouldn't have to worry about carries. Because we're working with 4-bit numbers. Let's try inputting Q times 2. And that, predictably enough, produces the wrong result. Okay. It produces the wrong result because Um, missing a step. Oh. Okay, actually what I want out of here. Okay. Okay. And the result of that is even more wrong. What exactly are they doing in this? Hmm? What are they doing? Assuming I'm reading this diagram right, which is entirely possible I'm not. Actually, I wonder if I should have been using an AND. That might make a big difference. Well, now we're getting a different wrong result. Okay. But it's less wronger, if that makes sense. Hello, Dread. Missing a step, I think. See if I can find a better example. Binary multiplication methods. Okay. Binary multiplier using the shift method. Parallel binary multiplier circuit. Ah, here we go. This one actually describes the same method, but with a much more clear diagram. Okay. Yeah. It shows all the inputs for an adder, including the carries. Using 3 adders, okay. Here. Let's go ahead and start this over. Use the token, it gave you 16 days? Oh, I thought it was only 14. Okay, cool. You get 3 beads. Maybe it's time to do the Imp Catcher quest. I think after those beads are 4. Also, they might be worth something, I don't know. Okay. The B0 is ANDed with A results and passed into an adder. Here, let's just go right ahead. Erase this whole circuit and start from scratch. Okay. Now, the first bit we want to do is we want to AND the first bit okay. Here you started it, just need to collect them to attack every NPC. Need to get to an area you can train agility. Get to at least level 5 so you can do the gold mining. You want to get level 30 agility quite early, because that helps a lot with run energy. Level 30 is relatively easy to get, and it's a kind of an early game sweet spot for having reasonable run energy without having to grind too hard. There should be a rooftop agility course in Draenor, I think. Where is the low-level rooftop agility course? Yeah, the Draenor Village course at level 10. Training before then. I think there's some easy quests you can do that'll get you to 10. I don't know if there's other easy quests that'll get you even higher or not. Okay. then we take all the bits in A, ANDed with B1 as well. Really? Seems like a weird... Not entirely sure I trust this diagram either. But we'll see. You know what I'm gonna do here? Gonna make this into a bus. Oops. There we go. Also, the rooftop courses are super helpful because you can get marks of grace from them. Which reminds me, I need to go farm more of those things because I'd really like to get the last part of the set. Oh well. Okay, those two results are then added together. But not directly. We need to do some bit splitting here. Okay. Wait a second. Like that. And this bit is left 0. So that's the one operand for adding. And the other operand is just this value raw. Boom. Get up high enough to do any courses, you need to go to the Gnome Stronghold and cannot figure out how to get there. Why would you need to go to the Gnome Stronghold? As you can train at level 1. There should be some quests that'll get your agility up to 10. Let's see here. You can go straight to level 3 just by doing 4 quests. Recruitment Drive, Tourist Trap, Death's Despair, and the Grand Tree. Recruitment Drive is pretty easy from what I remember. Tourist Trap. Don't remember what that one's like. That unlocks some other important stuff though too. Depths of Despair I don't remember at all either. And the Grand Tree will get you to the Gnome Stronghold. I don't remember what's required to start it though. Let me look. It requires 50, recommended 50 combat level. Items required is only 1,000 coins and 25 agility. You won't be able to do that right away. Oh, Gnome Stronghold. Okay, that might be actually easy to get to. You should just be able to run there from Artie. Okay. Okay, I'm starting to see how this works now. Why did I grab that? I should... Boom. Okay. And then this result goes to... It gets split up. Like that. And this bit goes to the output, which I should go ahead and make bit maker down here. This will be the eventual output. And then these bits are used to make another number. That one feeds into another adder, I think. And this result is the other operand for that add. Okay. And that result gets split again. It goes to there. Another byte maker. These need to get moved down because we're running out of room. And then we need our third adder. Its result once again another one of these. And this goes to there. That goes into another splitter. That should get us the rest of our result. We're doing 2 times 1 right now. Okay. That should work. We'll put an 8-bit maker down here for just so I can more easily have labels on the values. We're doing 1 times 8 is 8. 2 times 8, 16. And then 15 times 15, according to this, is 129, which I don't think is correct. Matter of fact, I'm quite sure that's not correct. Damn it. I keep hitting the wrong buttons. It's 225 is the actual answer. Okay. Why are we getting interesting wrong answers here? Let's do some simpler. 2 times 2 is 4. That's 8. 8 times 8 is 64, which is indeed correct, or should be anyway. Okay. One times 1 is 1. 3 times 3 is 9. Times 7. Should remember my times tables, I don't. I always was really bad at this. That is indeed correct, okay. But 15 times 15 is definitely not 129. Yeah. Okay, what is the problem here? Go ahead and do 14 times 14. And that is also wrong. Okay. Twelve times 12 came out right, though. $13 by 13 does not. Okay, what is the problem here? The carry flag is not set. Wait, where do the carries go from here? Ah, I forgot to hook the carries up, I bet. Because carry should be hooked to the 4th bit on the next adder. So to here. Which means I need to do some expansion of the system. Do some quick adjustment here quick. Fix some of these things. Go. Don't know if that's going to solve any of our problems, but... in this case, it's not. Now, are there anything other weirdnesses I missed? Yes. That's not supposed to be hooked up. Or is it? No, that's supposed to be hooked up. And this is supposed to be hooked up to there. Forgot how you get teleports to the main cities? Magic level. You just have to get your magic level high enough. You can also buy teleport tablets, which are kind of expensive. Or there's some other things that offer you teleports, various kinds of jewelry, which are basically a way to spend money on teleports. Will teleport you to some special things. I have infinite free teleports to Ardenug Monastery, for example, because I have a Ardenug Easy Diary cape. So if you do certain tasks around an area, sometimes you can get things that'll offer you benefits there, and one of the benefits offered by the Ardenug Easy Diary is teleports there. Things like that. But yeah, at 5 magic, you're not going to be teleporting much of anywhere. You get a lot of useful teleports before 50, though. Okay, anything else I'm missing hooking up? Wait a second. The carries don't get hooked up. I'm being a derp. That's with 4-bit adders. These are not 4-bit adders. These are 8-bit adders. So the carry is just the next bit. I should just hook those bits up from the beginning. Too real. Okay. Now. I want to move all of this up 1 notch. To there. Okay. We should have now 4-bit multiply. Oh, and we get a free byte multiply. Yay. Now we need to do divide, which is like multiply, but exciting. And we're expected to do it with the leg computer. which, yeah, screw this noise. We'll come back to it in a little bit. All right, push and pop. So, now, I think what I'm going to do here is we are going to re-architect this computer from the ground up. I like a lot of things about how this works. However, for my sanity, I like how clean it is too. But for the sake of my sanity, I am going to rebuild this to be a 2-operand instruction computer. And thinking about using 3-byte or 2-byte, I mean, instructions. The problem is, without a proper assembler, it might make way more sense to have 2 3-byte instructions. Can we even do that? I guess we could set the counter to advance by 3 every time. Yeah. That would be annoying. A lot. Also, I want to re-architect the bus to include all the flags as individual lines. Probably has both set and read lines. Basically have the flag registry be its whole area. That's gonna be really important to the whole system. I do like this IO bank. But anyway, let's go ahead and we will make a new schematic. First though, let's copy this one. New schematic. And we're going to call this one... Oh, I don't know. Naming things is hard. The problem is, it's not helped by the fact that leg is a really good pun. And so I feel like I have to do something at least as good. And the obvious alternative to leg is arm. The problem is that the reason leg is a really good pun is that ARM is a real CPU architecture. So that doesn't work very well. I think we'll just call it leg 2. I'm a boring person. Okay. These two need to go down here somewhere. That one goes there, I think. That one goes there. What in the world did I do here? I didn't end the bus there, did I? I must have. Oh, that already got deleted because it was off the bottom. Yeah, I think that section of bus got deleted because it was off the bottom. Well, that's an easy enough fix. Okay. Welcome to the Leg 2 architecture. Exactly the same as Leg 1. At least it is before we start making changes. And boy oh boy are we gonna make changes. As soon as I figure out exactly how I want to make them. So I think the best place to start with this is from the assembly. So I really want to do 2-byte instructions. Which means that each instruction has to carry one of its operands. Or we have to fit 2 operands into 1 byte. Now, that means the easiest way to do this is to have lots of implicit operands. Which implicit operands basically mean that you have registers who have a specific job. And while some of those registers can be used for general purpose stuff, they are always used. Well, okay, for example, we have an add instruction, let's say. The add instruction always takes from a specific register, takes its first operand from a specific register, always puts the result in a different specific register, and the operand is a third register or memory location or something similar that it deals with, for example. That's probably how we're going to do it. So I think I'm going to use an accumulator-based architecture. What an accumulator is a register that is usually the first operand for mathematical operations, and it's also the destination for mathematical operations. So when you add the operand to the accumulator, basically. So the accumulator, as you might imagine, is an incredibly important register. It is constantly getting trashed by everything you do. I think that's how we're going to do this. So we will have specific instructions for moving things into the accumulator. And then, of course, there will be a host of generic registers, but not very many of them because we don't need many registers. Most things we'll be doing will be accessing straight out of memory. And I'm going to use a lot of inspiration from half-remembered bits of how the 6502 worked. And when I say half-remembered, I mean exactly that, because I hardly remember how it worked. So, most of this is going to get trashed. Like, pretty much all of it. We need to change data width 8-bit, okay. Can I change this damn thing to only output 2 at a time? There was a thing I need to do to set the program. Oh, here we go. We're probably going to want to use fast RAM. Okay, we need to change the counter. Change PC to only increment by 2. Okay. That means we only have 2 lines in here. We basically need to delete the whole bus. Because we're going to be making a new bus. Let's just delete the whole top of the bus. And we'll lay out the new bus from there. Okay. So. Input. Don't know how we're going to handle that for now. PC is important. Opcode is important. Instead of having arg1 and arg2, we just have argument. What is going on with that? I wish you could tell this number, or this, damn it, I reversed it. I wish you could tell that not to display numbers on that wire. Maybe there's a way to do that. Okay. I kind of want to do the labels with a fancy color, but I'm rethinking that idea now. Nope, let's not do that. Okay, this is PC. the program counter. That's a somewhat important register. Zop. And that is ARG. Those are coming raw from somewhere and being fed raw into the system. Okay, now let's just close some tabs over here. Okay. Flags register. We are going to want to have flags for a bunch of conditions that may not make sense until it gets time to use them. Let's just lay out 8 of these. We're not going to use all of them. And we're probably going to have... Oh, let's see. Okay, the 6502 flags, I'm going to use this as inspiration for a second. They have carry 0 interrupt disable, which we don't need to worry about. Decimal, which we don't need to worry about because we're not doing BCD. Overflow and negative. I'm going to want a little bit more than that. And also less than that. Oh, and carry. Okay. So carry is extremely important. We do carry. Damn it. I did every single one of these backwards, didn't I? Alright, carry is set if we have a carry from an adder. Also, carry is used for doing subtraction. Let's not worry about that right now. 0 is set if the result of some kind of check is 0. That seems useless, but that flag is going to be used for jumps and stuff like that later. You can do, for example, subtracting in a loop, run a loop counter, and then you just do jump if 0, and that'll jump if the 0 flag is set. It's surprisingly useful. Let's see, what else do we have? Overflow. And I'm also going to do underflow. I need to make my labels longer if I do that. Oh, stop reversing things, damn you. Okay, fine, be that way. Okay, so these will be for stack overflows and underflows. Also for mathematical over and underflows. So if you subtract 1 from 0, either with an unsigned, it'll say underflow and the result will be 255. Let's see. I don't know if that's needed or not. There's also a negative in the 6502, which might be useful. And it won't be hard to set, and we've got lots of free bits, so let's go ahead and put something over there. We'll put it beside 0 in our architecture. That'll be set if the result has a high bit, basically. Not sure if overflow and underflow. I mean, it's useful for doing comparisons. I kind of want it for stack error signaling. I mean, carry already indicates integer excitement. These would be more for stack stuff. But if carry is sat, that's an integer overflow. Probably all we need. We don't need to worry about dealing with interrupts and stuff like that, so we don't need to worry about interrupt disable. So that doesn't need a flag. That'd be a thing you'd commonly spend a flag on. I think we'll just leave 3 blank flags for now, and we'll just accept that underflow is on probation. "15 agility and only have the red and yellow beads." You'll get them all eventually. Imps aren't hard to find. Okay, PC, of course, is being... Okay, there we go. Label this PC. Okay. Now we want to run a blue wire right beside these, which we're going to call flags. The problem is we're going to need 2 sets of flag pins. We're going to need 1 set that represents the current state as stored. That can be read from. And we need 1 set that can be set. So that's a lot of space to dedicate to one thing, however. They're going to be pretty important to the operation of the processor. So this will be the value. Actually, wait. Well, we don't do that. I should have deleted the other side. Oh well. These pins are for setting it. If anybody set these high, it'll set the appropriate flag. The flags... I should reverse these too. Damn it. There we go. Found a spot that 3 spawn regularly, but they like to tele away. I haven't killed imps in years, literally. I got all the really low level grind out of the way the last time I played back in, I think it was 2017. I don't remember for sure. Might have been before that. I shouldn't say the first time I played either. The first time I played this character, my current character. Okay. The reason why we want this like the way it is because we can just take an 8-bit maker. And I just realized... Okay, yeah, boom. Carry is bit 1, or bit 0, whatever. The ones place. I could have left it alone and assumed it was this way too. Everything else in the game reads from right to left, so why not? Alright. Now, what else do we need to have in this monstrosity? I kind of want this over here. I think we're gonna do hard V. Which is the value of the argument. Actually, no. Just because we're doing 2-byte instructions doesn't mean we're actually going to be using two-byte instructions internally, or 2-byte. So we want to have op select, op 1V, op 2V, and then we need actually destination as well, which we will call result. Okay, the operand, this will be the result of operand decoding. Yeah. Okay. Now, what did the old bus have on it? AK, am I missing anything? Jump enable. But that didn't really go on the bus per se. And we could do that in a flag if it felt appropriate. Because all jump enable really did is say that results should be copied to PC. Okay. Go ahead and extend the bus out a little bit. We could probably make the bus much more complicated. Or just spread things around a little bit. Go ahead and shorten this, actually. Move you in. There we go. We have the head of the computer created. Now, let's move this up considerably. We still have all the old circuitry down here. We'll go deal with that later. So, above this, I think we're actually going to build... Actually, let's move this down a little then. Okay. Where did you come from? Must have been misclick. Alright. Above this... I want to draw my bus going all the same way. Above this... I want to have the instruction decoding. Instruction decoding is not something we really previously had to worry about. Because the previous instructions were extremely simple. Actually, looking at this now, I think we're going to need another row or two. Because we need op 1 and op 2 as we need more than that. One, 2, 3, 4. Okay. Better draw these before I accidentally delete the headers I just made. Okay. We have op select. We have arg1 select. arg2 select. And result select. This should be named result v. And these should be named arg, not op. I was thinking operand, but op is already being used for opcode. So this will be a little less confusing. Okay. This is the new header. Goodbye, old header. Okay. So our job in this next block here is to take arg and op and turn them into the 4 values: op select, arg1 select, arg2 select, and result select. And then later we'll have another block whose job is to take those 4 values and turn them into the 3 values: result v, arg1 v, and arg2 v. Okay. In the case of invalid opcodes, we should also handle that somehow. Now the problem with my argument decoding is that I have no idea what the opcodes are going to look like yet. So, that is the next step. Let's just go ahead and ta-da! It's everyone's favorite text editor. Okay. Now for the real game. Opcodes. We definitely want addition. Let's take the opportunity to add the missing E to move. Addition and subtraction are 2 sides of the same coin. Okay, the thing is we can't really have, first of all, we need to find our registers. So first and most importantly, we have the A register. Let's have an I and a K register as well. The A register is the accumulator, doing the destination for almost everything. I and K are going to be indexing registers, which we'll get into that later. And then we will have flags, of course. PC isn't really a register but gets treated like one internally. Stack A, stack B will be stack addresses. Although stack A and stack B are going to also have to be... No, we're not doing a von Neumann architecture here. The stack A and stack B are going to be pointers into a separate section of stack memory. We're just going to set it to be fast RAM. Those will be accessible. The reason we're doing 2 stacks is because we'll get into that later. But 2 stacks is very important for some things. It's not very important for like C, but who gives a shit about C? It's a terrible language. Let's not call them A. Let's call them D and R. And let's here. This will be DP and RP. Okay. Let's try to keep register names short because that's going to be useful for labeling. I can put them on short wires easily. Okay. The accumulator, pair of indexing registers, flags register, program counter, stack registers, and let's see. A bank register, of course. We can address more than 256 bytes of memory. And then we'll have 8 general purpose registers. R0 to R7. So I have 8 special purpose registers. And then 8 general purpose registers. Although this is kind of a maybe kind of thing. We might just use memory for that. We might just go ahead and use memory for that. I'll think about it. Okay. That's the first concept out of the way. And then, of course, we will have memory. So the main memory will be at least 256 bytes with optional extra banks. And the bank register, or the bank index, basically, which one I want to talk to. Now, the previous version of the LEG architecture had an address register. I don't think we're going to do that. Use a fixed address register. Instead, we might use multiple registers to refer to main memory. You gotta sell these Marks of Grace? They're not tradable. You can, however, trade them for packages of amylase crystals, which are tradable. But what you really want out of them is the Graceful outfit, which reduces your carry weight. I would save your first 240 of them, I think it is, and get a full set of full Graceful outfit. Runelite lists the price for them, but that's their price based on trading them in for amylase crystals at the Rogue's Den. Rogue's Den? I think that's where it is. I don't remember what those crystals are used for. I think they're some kind of potion or something. Okay. So, let's start defining instructions. The first and simplest thing we need to define is how we're going to move things around. So we need to be able to move things from one register to another. Now, the way the LEG architecture did it is they had multiple operands, and each one stood for a destination. We're not going to be doing that. So let's start with loading stuff up. Load immediate. Since we don't have a true assembler, we can't do anything fancy with this either. Like have specific syntax for different styles of operand, having them assemble into different instructions which have the same name. We're going to have a separate instruction for every single actual hardware instruction. A lot of architectures have multiple hardware instructions that are alias to one name. We can't do that. So we have load immediate. I think we're going to call it LDA, actually. This isn't actually going to be load immediate. Well, okay. We'll have LDA. This will load parameter into A. How we're going to specify the parameter, I will have to decide later. But this will be loading from another register to A. And of course, I forgot I don't have my keybind set up properly on Windows. I need to fix that. Okay. Load the parameter as an mediate value into A. I call that LDAI, actually. Load A immediate. Then we will have SDA, or store the value in A to the parameter. Would help if I typed all the letters for that. Okay, so this will get stuff in and out of the A register. Which is going to be a lot of what we do. A lot of what we do is going to be loading things in and out of A. We'll load it into A and then we'll move it out of A to where it actually goes. A lot. Because anytime we do any calculation on something, it's going to be using A and storing to A. The port A register is going to get pretty hot from all the stuff going in and out of it. Let's put it that way. Now. That should handle most of the basic moving things around type stuff, actually. Except we'll have LDAM, which is load a value from memory. Into A. And SDAM, which is store a value in A to memory, where the parameter is the address, of course. Okay, we'll put these in a slightly different section. Also, we're going to have LD LDAMI Okay, let's just drop A from that. Load immediate, load to A, save A, load memory. Kind of like all that SD. We'll call it ST. Okay, load memory. Indirect, where we get the address from the parameter. Except I don't actually want to do it that way. Load memory indirect I. And I can't use my duplicate line hotkey because I don't have it set up on Windows. LDMK, which is load memory indirect K. So these refer to the I and K registers. And then value is an offset, or parameter is an offset. Okay. The idea for these is they would be used for things like array indexing. You would pass in the offset to the beginning of the array as a parameter, and then you would use I and K as indexes into said array. Basically, it's going to add the parameter to I and use the result as a memory address. Or if you just want to load something from an address stored in I, you would do LDMI 0. And of course, it's going to put the result into A, because everything puts its result into A. That's how an accumulator architecture works mostly. Okay. Now, jump. What is jump doing here? That seems like it has nothing to do with loading and storing. Well, jump copies the value in A to PC. And that is all it does. Very simple. It's a simple unconditional jump. And now we start getting into conditionals. CMP. Pairs to value, or pairs A to parameter, and yeah, we do need those GP registers, I've decided. Anyway, compares A to parameter and does not jump. It sets the flags. So that gives us the 0 flag, the negative flag, let's see. Not sure what else would have been set. I should look into how CMP is set on the 60. I remember how it... Basically, CMP is a subtract with sprinkles. Is all you really need to know right now. I don't remember if it sets any flags or anything first before it does subtract by default. Speaking of which, we're gonna have to get into setting more flags. But anyway. DayZ. Jump if 0 flag is set. I should list the flags in here. Okay. Now, what are my flags again? Carry 0. So how compare works, for example, to get equality, you subtract two numbers, and if the 0 flag is set, they were equal. Just as a for example. And if negative was set, or negative was not set, if 0 wasn't set, you can tell if it was greater than or less than, things like that. Because basically, at its heart, comparison is just a subtraction. Okay, we have a couple unused bits, as you might be able to tell. We have GNZ. Jump if 0 is not that. Okay. Okay, end. Jump if negative. Jump if not negative. Okay, we're likely going to alias these in various ways later. And there will probably be other jumps as well, but for now this will do. Okay. It immediately becomes obvious to me that I need to figure out a naming scheme for the registers internally. How many registers total do I have? 16? That means we can fit all the registers in a nibble. Which means technically we could pass 2 register IDs in ARG. So it would be possible to do a copy from general purpose register to general purpose register instruction. Or a copy from general purpose register to some other destination type instruction. Don't think we'll mess around with that just yet. But it will be possible. And we are going to have a whole load and store section. Okay. So this should handle everything but basic math. Ugh. Let's start doing math. Add A to the parameter store result in A. We have a very common pattern. Subtract. Subtract parameter from A. Store result in A. That operand order is pretty important because if we're doing loop counters, for example, what we're going to want to do for simplicity is we're going to want to set A to the number of iterations we want, and then subtract the step from A, and then check the 0 flag. That's an easy way to do that anyway. Okay. Multiply and divide, I'm going to skip for now. But they will exist eventually. As well as modulus, because that turns out to be surprisingly useful and important. But they'll be added later. Also, for subtract, we might have to do funny things with the carry flag for subtraction. Like subtract might require you to have the carry flag set before you do a subtraction. Yeah, we'll see. I think I'm going to divide my instructions into groups of 8 again. Or groups of no more than 8. Logically. So we won't try to cram the simple mathematics stuff together with shift left. Shift right. rotate left, and rotate right. It would help if I use the right vowel there as well. Once again, these will operate on the A register. Should have copied that before I changed the direction. Oh well. So we have shifts and rotates. We could probably add various variants of shifts and rotates. Yeah. If I remember correctly, there's some differences between arithmetic and logical shift. I don't know if I care about those right now, though. But for now, we just won't define any of that stuff. Remembering, of course, that we don't have to define the entire computer right now. We just have to define the parts that we care about. Okay, and stack stuff. Because after all, we do need push and pop. Push. And pop. Push R. Pop R. Because remember, we have two stack pointers. We have DP and RP. Okay. Push a value to the D stack increment DP. Set overflow if value after increment equals 0. Okay. Push value. Let's say push parameter. The D stack increment DP. Okay. The parameter can, of course, point to A. Because it would be possible to do add A to A, store result in A, but you would like never want to do that. I shouldn't say never. Pop a value from the D stack. Decrement DP. The overflow value after decrement is 255. Well, it looked weird. There was extra space in there. We'll allow popping directly from the stack to any register. Because that'll make it really easy to save and restore. Because after all, the whole point of using a stack is so that we'll be able to do function calls. And yeah. Also, we should have memory access instructions that use DP and RP. Probably just DP, actually. Let's add some more load instructions. LDDI. Load. Direct. D-stack. I. Parameter is offset. No. Yeah. No. We want a different register for that. We don't have an available register for that. We really want a register to be the frame pointer. We can have less general purpose registers. And assign one of the general purpose registers the job of being the frame pointer. Or give one of them an alias. Or I don't think we want to allow anyone to refer directly to addresses in the stack. No, well, that'd probably be fine. Damn it. Duplicate line isn't a thing. Load D-stack. Parameter is address. Load D indirect I. Load D indirect K. And we need to have store as well. It's going to be a separate block of instructions, because I just realized we forgot to define store and direct as well. Okay. Remembering, of course, that the value that we're storing or loading into is always A. It gives us 6 instructions in that block. Okay. That's a lot of instructions for dealing with the memory and stacks. The R stack is more restrictive. We don't allow randomly storing and writing to that stack. Also, we shouldn't allow offsetting by I and K. We need a different register for that. Let's just go ahead and 7 GP registers, R0 to R6. And then we have register FRM, indirect FRM. We'll still call it LDDI for load D indirect. Yeah. Actually, let's use F for frame. Okay, let's actually specify what our registers are. Okay. Bank select. Frame pointer. And then R0 through R6 are 7 general purpose registers. Okay. So, you may be wondering, why do we have a frame pointer? What is a frame pointer? A frame pointer is, it points to a spot in the stack and says from this point upward, we are using this memory as extra scratch space. And so you use it inside of a function to define local variables, basically. So when you enter a function, You push any registers you want to save onto the stack. Well, you set your frame pointer. You push any registers you want to save. And then you push any values you want to use as local variables. Possibly. If you need more than what you have registers available. And then you can access those variables directly by using good old LDDF or STDF or whatever version of a similar instruction the architecture you're using has, which is probably named something radically different. With the offset to your local variable. Pretty slick way to handle it. And then the next instruction to get called, he can save the frame pointer and set his own frame pointer, and he can have another frame on top of yours. Or if you're being recursive, you can have multiple copies of your frame, and so on. Now, there's nothing insisting that we have to have a 255 byte stack. We could make our stack much larger than that, and this simple 8-bit computer would handle it just fine. The only thing that would have to know about it being larger than that is the stack itself. It would mean that DP and RP could not be 8-bit pointers, but yeah, that's a problem for future Milo. For now, we'll just assume a 250 byte stack. If it turns out we have stack problems, we can always go ahead and change that. However, I highly doubt we'll do anything complicated enough that we'll end up with stack overflows. Anyway. Let's push. Put for the R stack. Using register RP. And same as pop, but for the R stack. Boom. All right. Now, what else do we need? Oh yes, reading and writing from I/O. We'll go ahead and add jump to this pile. We'll add I/O to the first block. LDIO. Store value in we could make an I/O register too and treat it that way. You know, I think there's something to be said for treating I/O like a register. So let's do 6 general purpose. R0 to R5. And we'll have an I/O register. Okay. So we have 16 registers. For now, we'll just represent them as numbers 0 to 16. Or 0 to 15, I mean. Which will actually allow us to store 2 in arguments, but we don't need to do that right now because none of our instructions need that. We have... ...32 instructions, actually. As currently set up. In 7 groups. We have plenty of room to expand. Okay. So that's the plan for leg 2. I'm going to put that up on the other monitor where I can look at it periodically. Just put a to-do to be implemented and be done. It's not that simple. Okay. Now let's go ahead and hide Sublime. Now, back to the game. Let's grab the level IO. And let's go ahead and do the simple task that I should have done a long time ago of turning these into a register alike. Okay. Ooh. File loader. Keyboard. Unix time in microseconds. That doesn't seem that useful. Network connection. 80 by 24 text character display. 6 by 8 dot matrix. 7 segment. Multi-layer sprite display. Looks like there's lots of fun things you can do in the sandbox. Actually, we could use these displays in here. Ooh. Okay. Okay. Different kinds of RAM. Yeah, who cares? Stops execution with a custom message. That might actually be useful in the case of extracts a byte from a wire. Oh, wait. This is actually huge. We could attach this to the flags bit and just grab whatever one we want. We wouldn't need to have all these separate lines. We could just have... It'd be less clearly documenting, though. Okay. I mean, I could do that anytime I wanted with a splitter, but... Okay, so we've got flags value. And this will be flag set. Ooh, that fits perfectly. Could not have planned that better out. Well, I could have planned it better myself, I guess. Really here. Let's move you down one spot. Move you up one spot. Boom. Boom. Okay. I want all these to be drugged downward because that seems to be less weird sometimes. Maybe drag all your wires the same way every single time. Go. All right. No. Cameo. There. Okay. So let's move this set of pins to there. Move this set of pins to there. So we neatly bracket these. And this can be the documentation station, so to speak. Delete those labels. Move that over. Okay. Boom. Boom. Okay. Now, I'm going to erase these labels actually, and erase these connections. And I'm going to grab this documentation block and bring it down to right here, like that. All right. Except, no, I don't want to do that. I was thinking about moving this over to the other side, but that would be weird with having to flip it over and then, yeah, no. Okay. Now, turning IO into a register. Go ahead and add a couple more segments here. the same way. That way if you have to label them somehow, they will go up properly. Go. Okay. Kind of wish that we could put these inside of a component, but that's not possible for a variety of reasons. So we have a pretty blue input line and a pretty blue output line. This is where we write the stuff we want to send to the level. We have a load line and a store line. Okay, load goes to there, and store goes to there. Ta-da, registrization completed. Can I run that down tighter? No, I can't. Okay. Not reasonably, anyway. This will get stuck somewhere in a register stack. We'll deal with that problem later. Now, finally got agility to 30. I spent an hour and 20 minutes running around rooftop. Agility training is so tedious. I want to say it's well worth it, because the amount of shortcuts you unlock over time is immense. It's just so nice when you can take the shortcut instead of having to go way out around sometimes. But man, is it ever a drag to get there in the first place. Okay. So we're probably going to use this basic pattern a lot. The IO banks, the bank select, and the bank output. The problem is I need to rearrange them around the new instructions. Those existing IO bank component are not going to be suitable. You know, I just realized this extracts a single bit. I don't suppose it has the decency to allow me to inject a single bit. That would be too easy. Oh well. I don't think we need anything else on this. All right. Computer core, done-ish. Next step, making the register banks. So, we want the IO bank select. We want a copy of it. We'll call it register select. Okay, now some things have to change big time. Okay, we've got 16 registers. We basically need a 4-bit decoder. We currently have a 3-bit decoder. However, that is a solvable problem. Because the solution is to make a 4-bit decoder. The I/O required for this is going to be insane. Two, 3, 4, 5, 6, 7, 8. Assuming we do it all in one go, which I don't think is a good idea. We could do this. That is a terrible idea, and I'm not going to do it. So, let's do a much more relaxed one. Let's do a 2-bit multiplexer to start with. Let's rename this. No, I didn't want to do that, actually. There we go. Two-bit mux. And then we want to add a pair of inputs. Just simple 1-bit inputs. We'll name this 1 and 2. Okay. Now, two bits gives us 4 possible states, conveniently represented here. Except, yeah, that's obviously not how we want to do that. Let me think about this for a minute. I don't think I want to do it using these simple decoders. I think what I want to do is use part of a 3-bit decoder. So just boom and boom. And that should be it. Now, why are we throwing away half the capacity? And what I really want is a 4-bit decoder. You know what? Actually, screw it. Let's go straight. No, I want this to be a multiplexer. Or do I? Yes, I do. And actually, I don't want these pins to be here. I want them to be up there. And there probably should be a 3rd enable pin. Which we're going to put up down on the other end. Somewhere. Okay, input. 8-bit input. 1, 2, 3, and 4. 8-bit. Nope, nope. IO. Output. 8-bit output. 1, 2, 3. No. You only want 1. Need to get 60 mining? A long road off. Okay, that's just 4 switches. Not that long, I guess. Depends how you're doing it. Personally, I'm a big fan of Motherlode Mine. But that's not necessarily the fastest or the best way to get fast mining. Well, it's definitely not the fastest, but it's pretty AFK, which I like. Okay. There we go. Let me do another input. No, not an 8-bit. 1-bit. I should have done this the other way so the text could fit on it. Okay. One problem solved. We'll move those up a little bit and then we'll put some off switches in here to fill this in. Okay. Oops. Okay, we got a 4-bit mux now. Well, a 2-bit mux, I mean. What I really need is a 4-bit mux. So for a 3-bit mux, we would combine 2 of these together. Okay. So change the name of this. Bit mux. Okay. So for the 4-bit mux, this should be select 1. This should be select 2. Let's select 3. Select 4. I1, I2, I3, I4. Now we have the fun and adventure. I'm pasting like a bazillion of these things. Okay. And the output pin goes over there. All right. And we just keep on going. Okay. Hopefully I actually use this damn thing. Custom. Just a row of 2-bit boxes that feed into another 2-bit box. Okay. And this runs all the way down here to there. This probably doesn't actually do what I want to do the way it's wired. This is a huge chip. Okay, the disable pin will go up this side, I think. Actually, wait. You don't need to run the disable pin to all those boxes. Nobody cares about them. We only care about the result of the last one. Speaking of which... There we go. 37 mining is pretty good. I'm not going to trade your 37 mining for my 92, but that is a grind I did not want to repeat just right away. Okay, if we select one, okay, bit 1 is hooked to bit 2. Okay. I was hoping this would output a 4. It does not output a 4. It still does not output a 4. Now, okay, yeah. Nothing on upwards. Yeah, duh. Here. There. Now. 1, 2. 3. And 4. So that's working. Now. To determine if we are accessing the other muxes in the correct order, need to remember that I cross-wired those. But you know what? Let's go fix that. Let's uncross-wire these. I'm just going to screw this up completely and make it not work. Then let's switch schematic to the 2-bit mux. And you are select 1. And you are select 2. Just the way it should have been from the start. Okay. Fill some empty spaces. Actually, yes, let's use off gates. Because they don't cost any gate complexity. No one cares how many off gates you have. Because they are quite literally just a gate that does nothing. The only thing we're using them for here is to fill out the body of the area that it makes sense to fill out. Okay. Now, whether or not I ever actually use this is a whole other story. But this will allow us to take 4 bits. Basically, this can be used for register selection. And I've just realized I need to make one of these for encoding, too. Decoding, I mean. So, let's create a new schematic. Bit decoder. Now for this one, we're going to use a 3-bit decoder. And that'll get us like 90% of the way there. Maybe. Let me think about this for a second. Well, let's say outer IO first before we get any too adventurous. We need inputs, 1 bits. 1, 2, 3, 4. And then somewhere way down here we have a disable. And then we have a shit ton of outputs. Two, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Boom. Okay. I'm tempted to have a single 16-bit output. They have a 16-bit splitter? No, they don't. Okay. Let's try to get all these spaced perfectly. Should be close enough, I think. Okay, that looks about as good as I'm going to get. So we can do the basic 3-bit decoder. However, they only just half the values. So what I really need is a 3-bit decoder for the high values, a 3-bit decoder for the low values, and a 1-bit decoder that enables or disables the other decoders. And then these 3 bits get directed into the decoder of our choice from there. Something like that. And then like that. And the end result should be pretty simple. Okay. What in the world is going on here? Oh, those are all up 1 for some reason. Wonder it's being weird. Okay. Now, this doesn't quite operate the way I would expect it to, which means we're going to want to adjust it slightly. And I know why it doesn't. I think what I actually want to do is use this bit for the disable. Actually, go ahead and disconnect those two. And then you get shifted across to there. Okay. So this counts up appropriately. When we set the fourth bit, it continues to count up appropriately. Okay, good. That's exactly what we want then. Okay, and then this disable bit disables both outputs unconditionally. So what we want to do is put in some ors. Like that. If this is set, that both decoders are disabled and ignores all inputs. This is very simple. Now we just need to add a shit ton of off switches to bulk it out. Because it would make perfect sense to have it so that it takes wires into account for the gate size. However, it does not do that. Also, we need to name all of these pins, which is going to be another nightmare. I missed a spot over here. Not that one. That one. Okay, there we go. Okay, you are officially 4, 3, 2, 1. Not that you'd be able to read those because this is a huge chip. I should prefix them with output. Also, they all need to be given the up output direction. Or the label direction, I mean. Okay. Wait, that was supposed to be a 10, not 11. That one's 11. Okay. And finally, out 16. And this is disable. And I missed one. Okay. They could do a better job about zooming components so you can actually read the damn text. But like there's space around it that could be used. Please, game. However, I'm pretty sure you're not supposed to make components this large and complicated. I say complicated, but I mean complicated in terms of pinouts. Okay. Glad you just got the 10 for completing the imp quest. Small step along a long journey. Okay, let's go back to our computer. And let's grab our fresh new monstrosity. If I can find it. 4-bit decoder. Can't read what anything does, but it's fairly obvious. 4 bits. Disable pin. Have you visited the Stronghold of Security yet? That's a solid, extremely easy 10,000 gold. Plus you get a decent pair of boots out of it too. If you have a, if you have 2-factor enabled on your account, I would strongly suggest just loading up on food and running past all the enemies through the Stronghold of Security. I think it has some combat level requirements for the later levels. But each level has a pretty decent cash reward, up to a total of 10,000 for all of them. And then at the bottom you get your choice of boots. This is probably going to be used for register select. Someday. For now, go ahead and move all this down a lot. And we're going to start building those registers. Oh wait, no. Before we build registers, we need to build instruction decoding. Just going to remove the documentation block in the middle of this because there's no need for it. It serves no useful purpose. Damn it, I knew that was going to happen. Really? I can't delete those? Yeah, I was going to say. Alright, I was just being weird about those couple there. I'm not sure what I'll put over here. Maybe nothing. Maybe I'll find something that goes appropriately in the core of the computer in the basic documentation area. We'll see. But above this, goes argument decode. I'm still not entirely sure how I want to structure that. Except this is where I'm going to define all of the instructions in the game. And where I'm going to set these 4 lines here. Result select, arg1, arg2, and op select. We could probably almost wire hard 1 to 0 for the value of the A register. But almost is not actually, so. Alright. So. Don't know if we need that up here. Next step. Instruction decoding. We're going to split it into banks. We're just going to use the 3-bit decoders because that keeps it in manageable chunks. Basically what we're going to do pick a byte splitter, put it right there. We'll run op in like that. And then we're going to have a long old bus along here of all the bits in the operand. No, we won't. We're going to have a pair of 3-bit decoders. This will be instruction group, instruction within the group. Yeah, that'll be good enough. And then we'll have 2 bits of throwaway. Which, those will probably end up going into a decoder later for even more shenanigans. Let's just go ahead and do it like this for now. So we have the high and low nibble are separate. And this way, should I ever get enough instructions that I run out of space on 3-bit decoders, we can switch to 4-bit decoders. for one or both channels without disturbing anything other than, you know, having to move everything apart. And rather than trying to drag these out a long distance, we're going to drag them a short distance, and then we're going to select the whole row and drag them out together. Also, I should have put one space between these so I could see the differences. Like that. Okay. You go way the hell out here somewhere. Because we're going to have a giant table in here of all the instructions in the game, starting from LDA. Also, you really do need to go up against the edge of the map. Okay. Now, the current bit pattern is for the instruction LDA. I'm starting to think the decoder was actually a bad idea. No, the decoder is a great idea. Because we only care about 2 bits in here. We care about this bit and that bit. And so we can just do and boom. If this is on, the instruction is LDA. And future instructions, we can just use ands with different combinations of knots attached. Let's actually make room for that right now. Boom. So this is the basic instruction decoder body. We just add knots or not, or don't add knots, depending on what the instruction sequence should be. Okay. So, LDA, the value we should be outputting. Okay. For each instruction, we're going to want 2 8-bit constants, one for the opcode, and one for the argument 1 or argument 2, as the case may be. Okay, so that's opcode, that's argument 1, that's argument 2, and that's result. Actually, it's more than... Well, here, we need some switches. 8-bit switches. And these little bus bars need to move up. We'll put them there for now. Okay. And these connect directly to the switches. These connect directly to there, and then these connect to wherever on the bus. And then we do this for every operand. Except there's no reason why op select has to be a different value from op. Yes, there is. Because we might share the same basic code for a couple different operations, just with different preset arguments. Okay. So we might have up to 3 of these. And every single instruction gets this. We probably don't necessarily have to do it this way. This is definitely going to get crammed into a corner and forgotten. As soon as it's all programmed. Boom, boom. Yeah, that's a lot of those. Now we need to enter in every instruction. I should subsequently move these down to there. And I also should draw a wire somewhere where I can write the instruction name. Okay, that's wrong. This is also wrong. Okay. There's the first 3 instructions in the sequence. They're all instruction group 0, and instruction 1, 2, 3, and so on from there. Okay. I should do a full block of all the possible instructions and then encode them. Okay. I probably should have 4 of these. No. No. I shouldn't. Well, I should have 4 switches. But one of them should go to... One of them should just branch ARG in. But that's not quite right either, because we should have a wire for ARG as a constant, and then a wire for ARG as a register number. I guess either way it doesn't matter. Except it kind of does matter. Oh. Problems. Fun and exciting problems. Okay. So I need to have a way to say if ARG1 select and ARG2 select should be a constant, which could be interpreted in various ways, or if it should be a register number. And then constants, depending on the instruction, will get interpreted as either like addresses or offsets or just straight up constant numbers or all kinds of random bullshit. Register numbers are always register numbers. Currently there's not really a way to do that. I almost need to add another pair of lines that specify that information. Let's see, I had 32 instructions. How many instruction blocks do I have? Yeah, I got 34 instruction blocks laid out already. So this would technically be enough space to code in all the instructions I've defined. Assuming I don't need to do anything more with this. I do think I need to add another switch to these though. Got 4 lines, we need to direct 4 switches into them. And I think I need to add more lines as well for using whether it's a constant or not. Or I could dedicate a couple of bytes in the instruction for that, like the leg architecture does. And that would work. However, I don't want to do that if I don't have to. And I would basically murder feature expandability if I did that. Because right now, all I need to do to expand this is add another row And then wire pin 8 to the disable on here. And then on the other row, I would wire pin 8 with a NOT gate. And boom, we have double the number of instructions we have available right now. So I don't want to limit the range of my constants either. Because the other thing I could do is say have a bit inside the select that specifies that, but that's a bad idea as well. So I think the solution is to go ahead and change it so that we have another switch. And then a couple, add 3 more switches to it. Using on and off things. We would do like this. And then have 2 more wires here, which would require us to add 2 more wires to the bus, which is not an insurmountable issue by any stretch of the imagination. Alternatively, we do have extra space on the flags, but that's dumb. No, we're not doing that. Because that's not... The flags are accessible to programs, so we don't want programs fiddling with their internal state. Okay. I'm gonna actually just go ahead and remove the bottom half here so I can save myself some effort, because we're not dealing with that yet. And I'm also going to move the top half down, because we figured out about how tall our instruction area is going to be. We'll likely have to extend it off on both sides of this to fit 32 of the new wider instruction definitions, but that'll be fine. Speaking of which, let's go ahead and get rid of some of these. Get some FPS back while we're at it. Okay. Go. Now, do I want to move these around? Yes, I do. Boom. And There's arg1 const and arg2 const. Let's name them. These are high. It means argument 1 and 2 are constant values instead of register. Where are our columns? Move those up, make room. Go ahead and paste these in. And those help make up the control lines for the computer. Okay. Select those wires. Zoom way the hell out. Select those wires again because we screwed it up. Okay. Now, more switches. Here we go. Now, not all of these switches are going to be used in all cases. Make these off signals by default. And we should reorganize these to be a little more sane. Oops, here. Grab that out. Grab that out. Actually. Okay, op select, arg1 select, arg1 const, arg2, yeah, okay, this is right. And then the result select. Result is always a register. So, of course. I go straight to result select. All right. Now, this instruction is one we did not define. It is the null instruction. It is do nothing. Now, some of these instructions are not going to use these constants. Some of them are going to be fed from other lines. I need to add those lines. Specifically, ARG might be used. Is that it? I think so. Okay. Occasionally you might grab ARG and drag it up to one of these. ARG 1 or ARG 2. Actually, I want to move this AND gate. I want the AND gate to be over here. Because if the AND gate is over here, oh, come on. There we go. Put this label over here beside the... I kind of want to run the label like this, so it's easier to read. Let's run it like that, so it doesn't obstruct anything. You might run a line underneath it, but that'll be fine, I think. Okay. Now for the first actual instruction. After we copy this block, and paste it a bazillion times. The game doesn't really like what I'm doing. Which is why, when I'm done defining this, I'm probably going to make this into an instruction decoder component. Okay, how many of these did I fit on a line? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. Yeah, that's not ideal. Well, this is half of the computer's worth of instructions, I guess. Let's lay one of these out. The problem is there's too many hard-coded-ish values here. To make this into a component. Because these have to all be inputs, and that just completely defeats the purpose. What I really need is a component that receives these two inputs and outputs these outputs. And has all 32 instructions hard-coded inside of it. So I should go do that. To that end, I'm going to make a simple documentation piece that I can bring along with me. And use to assemble the monstrosity. Okay. Yeah, performance is definitely chugging a little bit. And I'm hoping by moving this into a component, it will improve. It might make it worse. Guess we'll see. Okay. Grab ARG. Move it down a little bit. Boom. Okay. So this is going to be the basis for the new custom component. Copy that. Component factory. Switch schematic. New folder. Nope, I don't want a new folder. Switch schematic. New schematic. Leg 2. What is the name for this again? ISA. Okay, the idea of this is going to be full instruction set for the Leg 2 computer. Now, IO. We need some 8-bit inputs. Specifically, we need op. We need arg. Be impossible to read these. Because this is going to be a huge, humongous chip. It probably isn't even going to fit in the given area for it, but we're going to try very hard to make it. And then we need output pins that ideally I want to place along the same side. So, 8-bit outputs. Going to have a space, 2, 3, 4. Oh, let's put space between them. Actually, let's remove those. Okay. This is up so. This is ARG1 cell. And then we have a 1-bit ARG1 const. Then we have an 8-bit ARG2 cell. And then finally, well, not finally, but next, ARG2 const. Then last, but not necessarily least, we have result cell. Okay, now. Go. Now I'd like to jam this up in a corner. And add some offs for fill. I'm going to move each of these a little bit apart because we have plenty of space. But that's not the real reason, actually. The real reason is I want to be able to insert. Wait. Yeah. The real reason is I want to be able to insert off switches in here. Without totally screwing it. I hate that I have to do this to make it come out right, but needs must and all that. Now the real problem You know what? Let's just do this. Yeah, let's just do this. We can quite easily move these down and make a little bit of space that we need. Okay. That will allow us to insert an off right here. We just have to add the occasional off. To fill a gap. And technically we could probably grab all these and turn them and put them across the top. And make it even. Okay, now that I've thought of it. Let's just go ahead and do that very thing. Okay, they retained their names, they just need to have the direction of their label text changed. Okay. Boom. Okay, you are up select. Okay. Well, not do it that way, actually. Try a pin header right here that we can easily access. There. Minimum fuss and bother. Now, we do need either move those down or add a row of knots. And I know which I would prefer is to move them down. Alternatively, we could run them along the other side. No, that's going to be even harder. All right, we're right back to the we need to add knots problem. Unless we could just barely fit some in. Or not knots, but offs. Yeah, that would kind of work. Problem is this tile. We can fit one here in the bottom. Okay, that'll work. Okay. We've greatly minimized the number of offs we had to add to make the whole thing look reasonable. Let's proceed. There's a whole bunch of dirty hardware details. And we still haven't gotten to the actual encoding the instructions yet. Which is the whole purpose. Basically, we're making a gigantic lookup table. I say gigantic, but it's not actually gigantic. We're making a hardware lookup table. Okay. Get another one on the end. Nope. Okay. How many do we get in a row? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. Yay! Okay. Now. This is half of the instructions the computer needs. There's the missing one over here. No? Oh. There we go. Ta-da! Now, I want to make this only 2-bit. I can have 2 of these programmed differently. So this would be part 1 and the second one would be part 2. I think what I do here is I just remove those. And we keep it wired up as the way it is. And part 2 just has the second half. That would be a way to do it, for sure. You know what? I'm being done with these offs. If I move these all down. No. Damn it. I put the instruction name right there. That's a much better pattern. I have to make a second account for the Shield Arab? Why is that? Okay. You messed up the solo attempt, and now you need to have a player who's with Black Arms Gang, and apparently no Black Arms Gang members want to help. Is there a dedicated chat channel in game for organizing with that? I assume if there is, you probably already found it. I don't remember what I did in that quest. It was also much easier to find Phoenix Gang members. Really? Well, that sounds like an interesting predicament. What are the requirements for that anyway? Just some items. I'm pretty sure I finished that quest already, so I can't exactly help you. Otherwise, I definitely would. But I don't remember what I did for that quest. I must have got help in the channel in question. Oh, let's see. Am I all ready to start programming this? Not really. I need a second set of instructions. So the question is, do I want to do the second set here? Or do I want to do a second component? I think the answer is that I want to do a second component. So we should take an exact copy of this component as it lies exactly right now, and then define the first half of the instructions, and then we can define the second half of the instructions because they're going to use exactly the same. Oh, I would need to make these. We need to make these conditional outputs if I do two components. And then I would need to somehow decide if I should be outputting or not. Actually, a bit of a problem. Because that would be a whole extra wire, a whole extra switch for every single instruction defined. Okay, so let's not do that then. However, if I duplicate this, if I turn the corner with the outer rows here, and then do a row back on the bottom, we would definitely have enough instructions. You would have very limited room to expand. That should be a problem. I could run this back down here like this. But I need to have a switch somewhere. A simple diode would work. It'd be ideal if I could fit a diode in here. Oh, I can fit a diode in there. Okay. Then I can run a wire out this way and run that wire back. And this would be the should output wire, basically. We need to redo all the outputs though. That's a small price to pay, question mark? Be annoying as hell. Oh, let's go put these diodes in. I call them diodes, they're not really. They turn off states into undefined states. So they're a really easy way to allow you to run multiple wires together where you know where the wire is controlling itself, so to speak. You know only one of them is going to be on already. You don't need to insert logic to check. Okay. Now. Well, nothing for it but delete all these and redo it. Okay, I/O output 8-bit. Up select. Arg1 select. Arg1 const. Arg2 select. Arg2 const. Result select. Now let's go name them. Okay. And Arg2 font. And last, but not least, result select. Okay. Now, we just have a little bit more wiring. And then we'll be free to make a couple copies of this. And we should probably genericify them a little bit. Or fix the known bugs. Namely, make it so that they don't ignore the 2 unused bits. Okay. That bit disables that decoder, and that bit disables that decoder. In reality, those will someday feed into something else somewhere. I'm an idiot. I replaced all these with the normal outputs, not the switched outputs. Damn it, I have to do all that again. I'm never gonna get around to oops, that's not the right rotation for that. Okay, there we go. I am never going to actually get to the point where I am making this thing do anything useful. Okay. Let's rig the output disables. Or rather, the output enables. If any instruction is matched, it'll light this up. We just have to make sure that it never matches more than one instruction at a time. Which should be easy enough to do. Okay. Now, let's duplicate this. Gate cost is pretty high. Delay is quite low, though. Although I don't know if that's because nothing is hooked up yet or not. Okay, so where did Sublime Text go? LDA, load the parameter into A. So the registers, I'm just going to go ahead and assign them numbers right now. A is 0, I is 1, K is 2, flags is 3, PC is 4, BP is 5, RP is 6, bank is 7, frame is 8, IO is 9, and then 10 through 15 are the general purpose IO registers. Okay. Now, instructions. I'm going to assign these to groups. Group 1. Group 2. Group 3, I already assigned them to groups, I just didn't assign them names. Group 4. Group 7. Actually, this should be group 0. It's pretty important that we start from 0 for this because it's actually indexing. I did start from 0 on registers, yes. Okay. 2, 3, 4, 5, 0, 1, 2, 3, 4, 5, 6. 0, 1, 2, 3, 4, 5, 6. Okay. Okay. So we have 8 possible groups available with this current architecture. I should trim this down to we only have 16 in a thing. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Okay, so we have 1 too many. Boom. Okay. There we go. Trim off some extra wires. We won't trim these yet because we don't know who hooks to who yet. Not until I start wiring them up anyway. All right. Now, I did not name these outputs yet. Pop select. Arg1 select. What? Damn it. I screwed it all up now. Yep, because I removed it, it changed the order. And I spent a bunch of effort to make sure the order was correct. Alright, well, that's easy enough to fix. We haven't named these yet, so... Okay. Arg1 select. Arg1 const. Arg2 select. Arg2 const. And finally result select. Okay. Now, let's start encoding these instructions. So this is LDA. Load to A. To that end, we are selecting those lines. Oh shit. I just realized we have a problem here. Well, it's a problem that's fixable. Sort of. Yeah. Okay. We need to move that diode. Means this diode here is meaningless. In this case, it actually is acting like a diode. I don't know how I didn't see this problem before we got to the place where it was a problem, but oh well. Oh, fun. This is gonna make the... This is why I didn't want to have it down here. Let's see if I can fix it without having to have it down there. Okay, you can actually go down a little more. Problem is there's no open space around it. We could put it up there. Gotta jam it in. But that actually is an important value, so we don't want to hide it necessarily. This is where the problem of wires not bulking up a component becomes a problem. I wonder if there's a way to change that in settings somewhere. Doesn't look like it. Okay. That would be too useful, I suppose. Yeah. Alright. It's annoying, but it's not an insurmountable problem. We just have to move all this stuff down a little bit. Make room for the diodes below the AND gates. Okay. We just take these diodes and we squish them right up in there. Like that. Don't really like that positioning for them though. Problem with this is that they're blocking access to here, which might need to go down here to our... I'd like to be able to just drag a wire. And with this switch here, we can't. There's no other place to put it, though. Unless we change its facing. And that really can't work. I think we might just have to put up with it. Yeah. Okay, this isn't throwing off the footprint. Just going to be annoying. And annoying I can deal with. Oops. Damn it. Also fix all of these. I want them to be down one from where they're at. Okay. them all together. Okay. That is properly not causing everything to light up incorrectly. Now, LDA. Arg0, or Arg1, I mean, is 0 appropriately. It is the 0th instruction. So it is opselect 0. I need to assign all these instructions numbers too, don't I? Technically, I wouldn't have to. However, I'm just going to go ahead and assign them ordinal numbers. Except in cases where we have instructions that are the same instruction. If that makes sense. Oops. Anyway. We'll get around to that later. Actually, this would be an interesting opportunity to use an adder. Okay, 8-bit math adder. Boom. Okay, and then we need an 8-bit constant. Boom. Boom. Okay. Right now we're adding 0. 0, 1, 2, 3, 4, 5, 6, 7, 8. You know, I shouldn't be doing it this way. What I should be doing here instead is I should just be bridging the opcode directly across. Also, these don't need to be handled that way at all anymore. I think what I'm going to do is I'm going to remove all or most of these constants. I need another place to run a wire up through here and I can't. I don't have space for it. I guess I could space them all out a little tiny bit again, but... and that's going to be a pain in the butt. But what I really should do is run a wire through for op. I could run it up through here. Right through there, basically. And tie it into each of these. If anybody needs special snowflake behavior, oops, they can apply it themselves somehow. And I'll worry about it at the time. Oops. Okay, let's remove this bank idea. This way it will be possible to have opcode aliases, but realistically we're not going to have that. So this will be fine. Okay. Technically, we could just bridge this directly onto there. Boom. Turn op and op select. But just in case, we have a way to override it if we want to, and it's baked into the system. We would just need to run this around somehow and put a constant attached to this switch. Probably stick the constant up here and run it like that or something. Anyway, so this is LDA. LDA loads value, loads parameter into A. So register 0, parameter, which is another register. Boom. Result. Actually, let me think. Argument 2 is unused. Argument 1 is parameter. Finally got your measure to 20. Hey, break eventually work on getting range to 20. I was training range some last night up in on Fossil Island against the Nullmite crabs, because they have 100 HP and basically do no damage. Okay, LDI, load the parameter as immediate value into A. So we replace this off switch with an on switch, and we load parameter. Do it the other way around. Boom. Probably work on getting about 200 copper arrows and work up to iron and so on until range is at 20. I made like 16,000 mithril arrows last night. I had like 18,000 unfletched, or just on headless arrows in my inventory. My bank. Not even sure where they came from. I mean, obviously I made them, but when? And so I just I went to Blast Furnace and smithed out a whole pile of arrows. Store the value. Oh wait, no, I need to actually hook this up. This goes to there, and that goes to there. This continues to be a block 0 thing. Just like that. I should set these names so I don't forget what they are. This is LDI. And this one is STA. My fletching level is quite low and my smithing level is quite, cleaning level is pretty good. But I gained so many levels from making all that. I spent a whole hour at Blast Furnace almost exactly. Made several thousand bars of mithril just from stuff that had piled up from getting mining. Okay, STA is the next one. Store the value in A to parameter. So parameter is result. Okay. Now, group 1. Is memory management. LDM. STM. LDMI. LDMK. STMI. And STMK. And all of these are in group 1. I think where most of the headless arrows came from, now that I think about it, was I wanted to train some wood cutting for some reason. Oh, whoops. Okay, I was about to hook up the wrong one. This is the last one we need to hook up for that group. And so I just took a knife along with me and chopped willows for a while and turned them all into arrow shafts until I got bored. Or went to sleep, whichever happened first. And then I just bought a whole shit ton of feathers and at some point and feathered all the shafts and I just had them laying around. I should do that again. Because now I'm almost out of feathered shafts and eventually I'm going to want to make adamant arrows or something. Okay, so LDM. Load value from memory into A. So parameter 0 is A, or parameter 1 is A. Parameter 2 is an address. This hooks up like that. STM, store value in A to memory. So parameter 1 is going to be the address. Like that. So parameter 1 is the address, parameter 2 is basically we are moving Yeah. LDMI. Load memory indirect I. Actually, wait. I screwed this up. LDM is loading to memory. The result is memory address. Except we don't want to set result. Because we can't mark result as a constant. Yeah. We pass a constant in parameter 2. And for STM, store value in A to memory. We should do the same parameter order. And handle it in the move circuitry. Okay. Now, LDMI is load memory indirect I. So, register I is register 1. So we go ahead and set that to 1. A is register 2, so let's go ahead and set that ahead of time. And then these values are the addresses, or the offsets. Like that. Okay, result is unused for all of these memory instructions, basically. Because we don't have it configured to store a constant result. And it doesn't make sense anyway. The result is unused. Now, STMI. Stored memory indirect I. Okay. The store instructions require 3 parameters. They're not like the load. The stores actually, I think for the stores, actually, I just realized something. We can't do indirect stores. Yeah, we can. Because we're storing A. Like always. This is 1. This is 2. Yeah. Yeah, we're always dealing with register A. Nearly always. Like LDMI, we're loading to register A. So technically you could kind of consider result, which is currently set to 0, to be where we want to store to for those instructions. And I might even use it for that when we get to that point. But anyway, STMK is done. Now, group 2. Group 2 has 4 instructions. For now, anyway. Expanding this is going to be a pain in the butt. But no one ever said we had to put all the instructions in the group in contiguous sections, so... Now... LDD, LDDF, STD, STDF is group 2. LDD, LDDF, load D frame, store D, and store D frame. Laying out like the more modern hardware. I don't know about more modern hardware, but this is kind of what I've got going here. We're doing an accumulator architecture right now. So almost everything's passing through A. More modern than what like Leg is emulating. Maybe a little. I am being heavily influenced by my vague memories of what little I knew about the 6502. I've never actually programmed a 65. Well, I have programmed an emulated 65 LO 60 something or another with that 16-bit extensions for the 6502, whatever it's called again. But anyway, we've got an accumulator, we have index registers, we have flags, 2 stack pointers, memory bank selectors, frame pointer, a few general purpose registers, because of course you need a few of those. We only have a few flags defined right now, and then we have, there are currently 32 instructions, but I'm sure I'll add to that as time goes on. So we have basic loads to load into the A register, dealing with memory, dealing with the data pointers, basically dealing with the D stack. The R stack is more restrictive, largely because I didn't feel like doing a whole set of instructions for the R stack when its purpose is not to be used that way. Jump and comparisons. These are subject to change quite a bit, probably. Basic arithmetic, more basic arithmetic. I don't have any and, or, and that kind of stuff defined in here, which I need to do that. And then, of course, push and pop for both. I should move this stuff up to the actual dealing with the stack. Make that group 3. Actually make this group 7. And then group 6. Damn it, I keep forgetting I don't have my hotkeys set up on Windows. Oh well. Alright, just to be like... And... Or... Dot... XOR. We're going to need a third bank of instructions for this, though. Anyway. Sublime? Oh, I see. When I minimize Sublime, it stopped capturing it. Alright, whatever. Daily Linux? I use it for work. So, pretty much every day, yeah. Yeah, that was Sublime. That's my normal editor for work. And for everything else. Used it long before I got this job, or any job doing programming for that matter. But I spent a lot more time customizing my controls properly over on the Linux side of things than I have over here. Okay. I need to have Sublime up in the other monitor so I can see what instructions I'm implementing. Okay. LDD. Which is load the D stack. Parameter is an address. So this is basically just LDA. Okay. And then LDDF is load to D, do the frame pointer. The frame pointer is register 8. Okay. And then this is store to D. This is store to DF, which means this is register 8 again. I've never tried to run this on Linux, because I don't game over there. For multiple reasons. The main reason is because I don't want to pollute my work environment with games. The other reason is because I don't want to mess up my setup. I would happily switch to Linux for daily driver, for everything, including streaming, if I had another computer to experiment with. I'm not going to set this thing up to triple boot. I actually have a physical switch on my desk. This thing's really cool. This switch is not plugged in right now, which I need to plug it in before tomorrow. If it's in that position, my computer boots Linux, and in that position it boots Windows. If it's in the middle, it goes to grub. I unplugged it so I could plug something else into that port. It's a little Raspberry Pi, whatever it's called. The microcontroller one. A 2040 or whatever, I don't remember what they're called. It's a I think it's a Pi 2040 is the actual chip. I don't remember what the board is called. But it's pretending to be a mass storage device. And when the switch flips, it changes byte inside the file on the mass storage device. And then Grub mounts it and reads that file and decides what to boot. It makes my daily reboots to go back and forth between Linux and Windows just a little tiny bit more slick. Okay. STDF. We are getting a parameter and register 8. And the result goes to the dstack, but result is not set in this case. Yeah. Or rather, we're going to ignore the result that is set. Now, we can fit 3 more instructions into this block. And we don't have any room for that. So that is the end of this block. Got a little bit of room out here for expansion, should we ever need it. Okay. And now I realize I should have made a copy of this before I started setting up instructions. We do have a copy of this before I started setting up instructions, but it's not the latest version of this. So it's missing some important features. Oops. Alright. Switch schematic. Let's delete part 2, because it's too old to be useful. Yes. Duplicate part 1. Rename part 2. Leg ISA part 2. Now. Go ahead and delete these wire comments. In this case, it's just a little piece of wire that I'm using to label the block so I can remember what instruction it's for. Okay. I probably should use a different color wire. Alright, now, the other thing we need to do, delete all these connections. Oops. These are going to be some massive custom components. They don't even have very many inputs or anything. The reason I'm doing it in custom components is so that hopefully the performance of the main computer when just looking at it isn't so bad. I'm hoping it bakes them into something or other, and maybe the rendering or who knows what. But I'm hoping it'll be better. So I started defining a bunch of instructions in this manner. And it didn't like it. Game's performance is a little bit iffy sometimes. I've noticed. I'm just going to go ahead and delete all these. Actually, wait, no. These are correct. Delete all the ones that aren't blank. Just basically all of them from here out. Hello, Treebeard. I don't know about my dream computer. My dream computer is definitely a lot more complicated than this. And it's definitely not 8-bit. But I'm building a computer. And it's significantly different from what they were trying to get me to build earlier. Get rid of these extra pins. Okay. Now this time, once I'm done resetting this, I should go in and save a copy of it, a clean copy. So that for the next row, won't have to do anything like this. Alright, let's do that right now. This is clean now, right? Yes. Okay, good. Boom. Duplicate. Okay. Now, we finished group 2. The first 3 groups are done. Group 0, 1, and 2. We have 3, 4, 5, 6, and 7 left to define. All right. Now, we're starting group 3, which is push, pop, push R, pop R. There's 4 of these, and they do not connect to that wire. This is group 3, so 0, 1, 2, 3. Now we have 2 free pins here that are currently wired to disable pins. That's so that if I want to extend the instruction set even more beyond what this blueprint would allow, I would just have to do a little bit of shifting around. And invert, basically I would just have to invert these pins. And I would have a whole second set of instructions. Allowable instructions. Instruction set architecture. So like ARM is an ISA. RISC-V is an ISA. Also, why did I just hook that up like that? They don't get hooked up like that. They hooked up like this. Okay. We're wasting massive amounts of the instruction set. Area, basically. I'm okay with that. because these subchips are defining the instruction set of the computer. What these are doing collectively, they're gonna have to be wired in as a group. They're taking our 2-byte opcodes, which the first byte is called op, the second one is called arg, and they're turning those into these wires: op select, arg1 select, arg1 constant, arg2 select, arg2 constant, and result select. Basically, I'm halving the instruction size of the leg. And even then, I'm wasting bits. A lot of bits. If this was a real computer, we would have a variable size instruction, and yeah. Yeah, so these are called leg 2 ISA because these are defining the ISA for the leg 2. Or its instruction set. You can have multiple different kinds of processors that use the same ISA, but then they will speak the same language, so to speak. So, like, most desktop computers use the Intel x86, or, well, it'd actually be the AMD 64 ISA. But anyway, we could definitely have lots of 1-byte instructions, but then I'd have to deal with variable byte, variable size instruction decoding, and which actually wouldn't be that hard. I would just have to have some instructions also increment PC, and then we just have PC normally increment by 1. It'd be a pain in the ass. A completely avoidable pain in the ass by just wasting some memory. However, that's the kind of thing you would worry about back when these computers were new. Or, 8-bit computers were new. Alright, let's start actually naming these things. Push pop, push R, pop R. Okay. Push. Pop. Push R. Pop R. Okay. So push a parameter to the D stack, increment DP, and set overflow on possibly. We don't need to change anything about this because all of this is meaningless. Arg is just going to be set to 0. Actually, no. Okay. I'm thinking like push A, but no, we don't want to do that. We want to push the argument. So we actually do want to hook this. Argument 1 gets hooked to the arg value, which should be a register. That way we can push any register, which will make saving registers very easy. Oh wait, not for pop though. And push R is the same way. Push any register to the R stack. The reason we have D and R stacks is because I like it that way. When your Amiga 500 was new, yeah, that's when you would have worried about that kind of stuff. Oh, let's see. Pop a value from D stack, store to parameter, and decrement DP. Okay, so we do actually want to run pop the same way. Boom. And boom. Okay. Actually, we don't want to run pop the same way. We want to run pop the result. Yeah. Because these arguments have special meaning. It's actually going to go grab a value out of a register and put it onto a different line on the bus, depending on what's in here. Which is actually why we need these argument 2 const and argument 1 const lines. They tell the later register code, don't go loading, or they actually tell it to bridge these values directly onto the arg1 val, arg1v and arg2v, which are bus lines in the main computer. If these lines aren't lit, then it means that you're supposed to look up the register. The register code should grab the register specified in arg1 cell and put that onto arg1v. So if you're actually passing parameters in these as constant, I really should be setting constant. I really need to be. Okay, popr is wired. All right, next up. Next group. Jump, compare, jump 0, jump not 0, jump negative, jump not negative. Okay. CMP. CMP, compare, notably, is just subtraction. It's subtraction that throws the result away, but it's just subtraction. So basically you're just doing a subtract without storing the result anywhere. It gets discarded. And all you care about is how it sets the flags. Okay. J0. Jump not 0. Jump negative. Jump not negative. I probably should change the names of some of these. Because like jump negative and jump not negative should probably be greater than and less than. Jump 0 is literally equals. Jump not 0 is literally not equals. But anyway. And then we should probably end up making a couple more. Let's see, how many of these do we have? 1, 2, 3, 4, 5, 6. We have room for 2 more. So we could do jump if 0 and negative. Or jump if not 0 and negative. And that would be less than whatever. I had to figure it all out. I think I am going to leave 2 blank spaces in here for future jumps. I'm going to call these reserved. And we're not going to hook them up. Okay. So these are group 4. 0, 1, 2, 3, 4. Except down here. Oops. 0, 1, 2, 3, and 4. Boom. Spot on. Okay. And we just keep running on across. We'll hook up these pins of the reserved ones. Actually, we'll probably just hook the reserved ones up completely, as far as that goes. But they will just be undefined instructions that don't do anything. Okay. Line 1, line 2, line 3, line 4, line 5, 6, line 7, and line 8. Okay, jump. Jump is an unconditional jump into the void. And it just copies the value in A to the program counter. So leave that to 0. What is the program counter's register? Let's see, PC 4. Okay, PC is register 4. Actually, no, wait, that's wrong. I mean, that's PC's register, but that goes in result. That's where we're copying it. Okay, compare. We take the value in A. We take the value passed in an argument. We subtract them. And we do nothing with the result. But we set the flags. Yeah. Compare A, parameter, set flags, but since we can't set result to nothing, we just set it to A. On some older computers, it would literally have used the ALU using the same exact circuitry as subtract, just with some per bit flip to tell it to void it instead of writing it to someplace useful. Okay, jump 0. Jump at the 0 flag is set. Jump to the parameter. And parameter... Actually... Do we want to require it to jump to someplace that's stored in the A register, or do we want to jump to someplace that's stored in any register? Well, that's not too hard of a decision. Let's let it jump to any register. Or based on any register. And all the rest of these jump instructions are basically the same exact thing. Just the only difference is the condition. And the reserved ones don't get hooked up. Okay. So that handles the conditionals. Now we have add, sub, all, div, and mod. That's 5 more. We only have 4 more slots, so we're done with this one. We could do shifts in here. But what if I ever want to add arithmetic shift and that kind of stuff later? It doesn't hurt to add more of these components. Yeah. I think we'll just leave some space. Really, I should have been leaving space from the get-go. Because each of these is 16 things long. I could just assign 2 groups to each one, instead of putting 3 groups in the first one and continuing bad habits from there. don't really want to go back and fix that, though. Yeah, I really don't want to go back and fix that. Future me is going to be very annoyed with current me if I don't, however. We will need to make 4 of these if we do that. That's not really a problem. Okay. Let's go back to part 1. How many parameter? Okay, first one's only 3. Yeah, we'd have to copy... Oh, let's see. These 3 are the only ones in the first group. We'd have to copy the rest of these out, replace them with blanks. Let's see. LDD is the first one of the next group. We'd have to copy these 3 off, or these 4 off, and move them to another one. Okay, you know what? Let's duplicate the template. Let's rename it. Okay, can't have an and symbol in there, probably because file system character limit names things. Okay. Now. Let's see. Switch schematic. Back to part 1. Grab the first 3. Like that. Delete the parts that are going to matter. And there we go. Okay, now 1, 2, 3, there's 4. 5, 6, 7, and 8. I should go into the template and wire these, like wire the second leg but not the first leg. And honestly, I could do a much better job of how I rig this up too, so I don't have to wire all these manually every time. Instead of having the full 8 down here, I could just run 2 across. Well, I do believe I am going to do that. Have I screwed this one up. You go down to the third one. The perfect is the enemy of the good, but you know what? Screw that noise. Okay. And you go to there. Then we delete those two lines. Then, what we're going to do here is make little nubs right there. Select this bottom row. Oh, I see what the problem is. Make a second row of little nubs. There we go. Okay. Put pins there to enforce that staying in position. Okay, this is what we're going to do in the template. And then the template, we can just change which pins these connect to. Okay. Now, let's go to the template. It's magic. That murdered a lot of otherwise useless wires that will never be used. I guess that's what useless means. Okay. Those to there. Now. This pin goes to the bottom. And then these connect like that. All the way across. This will make it easy to expand the architecture in the future. Okay, and then this is the last one for the first bank. The second one goes to the second set of pins. And repeat the process over again. Okay. All right. Now let's even trim the wires, because why not? Now, we need to grab the second segment. So group 2 is LDD to STDF. No. Yeah, that's group 2. We need group 1 though. LDM to STMK. Okay, there we go. This needs to be renamed to 0 and 1 as well. From those. Okay, this is the last one for the first group. So this means this is the first one. How many of these do I need? 6. So all but the last 2 have their mode stripped. Okay. Of course, the values, this stuff doesn't quite line up. Most of it does. Go ahead and set the pins. Okay. Now, make sure these are wired correctly. No lingering weirdness. All right. That looks good. Now, we duplicate the template. And then we have parts 2 to 3. Okay, the next bit we need is LDD to STDF. there. Switch over to part 2 and 3. And we just paste this down here, off in the middle of nowhere. I can make a few important changes before I go pasting it in and making a mess. Okay, this is 4 instructions, so we'll clear space for 4 instructions here at the beginning. Also, we need to rewire this bit. We got 0 and 1 out of the way, so this is 2 and 3. Okay, that should be 4 cleared instructions. Remove those nameplate wires just to be safe. Repin these. Beautiful. Okay. Now, part 1 is used up. Into part 2. So now we need group 3. Push pop, push R, pop R. Which is this. And paste this in down here. Give it a little light pruning. Over here. First instruction on the second group is here. We need 4 of these. Like so. Repin. And clean up. And we got that in the right spot because we have 4 empty instructions after it. Okay, so this part is done. Yeah. So we go back here, we take the template, duplicate it, name it. This is part 4 and 5. Go ahead and enter it. We need to go over here and rewire. Part 4 and 5. Then we just have 6 and 7 left after this. Okay. Now, this is the section we just did. JMP, and these two reserved, all the way to these two reserved ones. Okay. This is group 4. Go ahead and paste it in down here so we can prune it. Anything that connects to the AND gates needs to go. Okay. Then we need to delete all of the instruction parameters from the entire first set of 8. Well, technically not. We need 6 clear. So 1, 2, 3, 4, 5. We're not gonna bother placing 2 reserved ones in. They aren't useful. Okay. That all lines up nicely. In these. Delete that. Get rid of these old ones. Okay. That was group 4. Now let's go get group 5. I don't think we ever actually did. Let's just double check. Yep, okay, that was the end of what we had done already. So we can delete part 2. Okay. 0 through 1, 2 through 3, 4 through 5. Now we do group 5, which is add sub mul div mod. Starting with this right here. Add sub mul then div. Oops. Or multiply. Modulus. And there should be 3 left over. Yep. Okay. So add is add A to parameter, store result back in A. We delete this and connect. Sub is subtract parameter from A. So A minus parameter, store in A. Mul, same deal. Div, same deal. Modulus, same deal. Okay. Very simple. Very straightforward. over here is where I would add instructions for if I wanted to do an add immediate or subtract immediate instruction, which would be quite useful for doing loop counters and stuff, and I might add them later. But for now, matter of fact, due to the way this is architected, doing add immediate would not actually require me to add an extra opcode. I mean, I'd have to add another opcode, but I wouldn't have to change the machine outside of this. I could just go into here, delete the line where this is hooked to the opcode line, and have it send the same opcode as it would send for add. And then do the add immediate. Tweak a few bits in here to make it accept this as an immediate value and go on from there. I'm tempted to do that right now just to show how it'd be done. Nah, screw it, we'll do it later. Or maybe we won't. Then group 6, which is in the next area, is shifts. Can I combine those with anything else? We could combine group 6 and 7 together quite easily. Nah, we'll do that later. Alright, so let's schematic. Duplicate. Rename. 6 through 7. So making it so we can go beyond group 7 is actually pretty trivial. And I already designed to allow that. The same as I already designed to allow adding more than 8 instructions in a group. I would probably actually make it so I could add more groups yet than that instead of... like, I'd probably reuse those bits in a different way. But I highly doubt I'd need more than 64 instructions with the boy computer as it is. Okay, so we're in the 6 and 7. Which means we need to rerun these. Okay. See, this unused pin is wired to disable. So all we would need to do is take this and invert this pin, and we would have a whole second set of groups just with that pin inverted. And then we could do another whole set for the upper half of group 1 through 16 again by just inverting this pin as well. So we do have access to the entire address space. We just have to flop some pins around. Okay, so... and we don't have to go back and modify any of our previous work to make it work either. We can just go ahead and add more groups as we need. I highly doubt we will need. Group 6, and/or not and XOR. And or not an XOR. Okay, so and is just like we've done a bazillion times before. A and argument store in A. And so are all the rest of these. They're all exactly the same as far as their parameters go. Except not. Not does not need a second parameter. Or any parameters for that matter. Well, it needs A. It just inverts the A register is all not does. Okay, and then group 7 is shift left, shift right, rotate left, rotate right. So let's scroll over here and find the first one of group 7. Boom. Shift left. Shift right. Rotate left. Rotate right. And these are exactly the same. Take the value in A and rotate it by the parameter, or shift it by the parameter, or whatever. These are extremely trivial to hook up. Okay, and we have defined the entire ISA as it stands right now for the leg V2, which I called that because I couldn't think of something more clever to call it. All right, finally. Now where were we? Push and pop. Okay, let's just delete this baby instruction decoder that never actually went anywhere yet. Game really didn't like that. Don't know why it's having so many performance problems. If they want you to build a computer, you'd think they'd put a lot more effort into making sure you could build a computer. Okay. I'm gonna hope it's a rendering problem. Okay. Oh, you can read the text on it reasonably well. Good. Okay. So there is the instruction decoder for the leg. And I don't think the game likes this any better than it liked its previous adventure. So my big hope that putting them all into this format would save my frame rate appears to have not come to fruition. Okay. Now, I definitely cannot read what those pins are supposed to be. So I'm going to have to go by memory. So this should be op select. Thankfully I did them in bus order. So op select, arg1, And since the pins are different sizes, we can also tell right where they go. Question is, which of these is op and which is arg? And that is a good question. Because that is one problem that this game does have with its custom. Well, this game has a couple. The whole custom circuit thing in this game is a little bit janky. It doesn't actually work all that well. For anything more complicated than very simple tiny gates with 1 or 2 inputs and outputs. Okay. That should be good enough. So this one will actually energize the line. Because currently we're requesting to load register A to register A. In other words, the null instruction. I'm going to assume the gate score is 666. Oh no! Let's see. Arg is the bottom, op is the top. Okay. So this one's arg. This one's op. I've spawned the PC devil. Apparently. Are they all gate? Score 666? So they are. Okay. I guess it makes sense that they're exactly the same gate score, because the only difference is how they're wired. Well, I guess we have discovered the gates of evil. Okay, let's just move that up a little bit. I'm going to try restarting the game, because this is chugging really hard. And I'm not sure if it's my computer or if it's the game having a subtle memory leak or something. If it's the game, then that's a serious issue for my dreams of massive computers. Okay, that is immediately way better. It must have been a memory leak somewhere. Okay. So, we have instruction decoding finished. That is the easy part. Sort of. The next thing to do is the registers. And from the registers, we will take these values and turn them into these values. And handle these values as well while we're at it. The rest of this, and this little bit over here, PC, are what we need to handle next. Hello, Kirk. Welcome here. So, registers will go somewhere. We're not handling registers together with RAM this time, I don't think. And we're not going to handle registers the same way we did here, where we had 3 custom components that work together. Optionally without the middle one. Although this part, the bank select and the bank output, kind of made sense. Oh! Let me think. So what we really want here we have let's do the registers right down here, right below the monitor. We have 16 registers defined. We have the accumulator. We have index register I and index register K. The flags, which technically get stored in a register, but we're not going to store the flags in an 8-bit register, I don't think. The flags is kind of a weird special case. We're probably going to store that in 1-bit memory modules and assemble the value to go out onto the bus, because flags is going to get its whole separate area to handle it. It's complicated. Okay. And then we have program counter, which is another special purpose register that is not actually a register. And then we have the dstack pointer, which isn't really a pointer because it doesn't point to main memory. It points into the dstack memory, because the stacks are each going to have their own separate memory segments. We have the rstack pointer. Basically, program memory, stack memory, and main memory are going to be 3 separate places for a reason. Have bank select, which may or may not be a special register. The frame pointer, which is just a normal old register. The level IO, which is definitely not a normal register. That's this up here. And then 6 GP registers. Okay. So we have, just looking at this little list I made here, we have 3 special registers and one sort of special register, which was the flags and PC are these. R&D stack, the bank select. Okay, we did make some special chips for this. Where did they give Wonder off to? We have a 4-bit decoder. That may come in handy. And we have a 4-bit MUX, which also may come in handy for making the registers. Because technically all the register numbers we don't have any, we have only 16 registers, so these should do the job, what we need to do. Thank you very much for the follow, Marximus Maximus. Greatly appreciate it. Okay, so kind of wish I would have designed this so that all of the special purpose registers were in a group somewhere, but I didn't. I just laid it out in an order that made sense at the time, shall we say. Okay. So we need a byte splitter. Wait, I think this... Yep. This is pin 1. Damn it. Why do I do these things to myself? There we go. Now technically I should make sure all these pins are unset. You have a question about electricity. I am not necessarily the person to ask that. Because I am far from an expert on electricity, to say the least. Let's do... this. Ah, shit, this needs to be moved back one more. Okay, if any of those bits are set, then we turn the decoder off because the value is invalid. This should select registers for, say, writing or whatever. Or reading. Now, we would use 2 of these, I think, to gather all the registers and send them to arg2v or arg1v. This way we don't have to worry about any collisions or anything. We can just set all the registers to read all the time. And we can feed result Wait, why do I have result V? That makes no sense. Yeah, that does too make sense, because that's the value coming into store. Okay. So these are selecting, this will select a register to write based on result select. Yeah, let's grab these registers and move them. We will do something with them eventually. We'll just hook this up temporarily so I can see what's going on. Result select will run into that. Also, program counter needs to go in over here somewhere. Let's see. Flags, PC, program counter goes right in here. I'm just a normal register, guys. It kind of almost fits in where a normal register would go. A little fat, maybe. Anyway. Okay. And then this would go over top of the registers, and all of them would run to the middle and hook to that. And then that comes out. We have one. This is way too high up. Go. There. That hooks to arg1v. Let me grab another one of those. And that hooks to arg2v. Can we get Milo design circuit cards? I don't think so. This kind of thing is fun. Designing things that use actual electricity to do things are less fun. Because then you have to deal with all the dirty real-world details. Okay. And then result V goes in across the bottom of the registers and hooks to their inputs. Yeah. Wait, no, this is where PC goes. Level IO goes down here. Reminds me, I need to go grab PC and get it up here. Okay. Here's our lovely friend, the program counter. He goes right in here, where he tries real hard to pretend he belongs. He's got most of the same inputs. He just doesn't have a load input because he's always outputting. Which is part of why we need these muxes. We could put a switch on. But now he has a normal register. We don't want to actually do that though. Because this needs to be run out to the bus and hook onto the PC line, which goes to the actual program memory. Okay, so the only special purpose register we don't have in this lineup is the flags register. because that way lieth insanity. Oh, piece of shit. I hate when it does that. It doesn't let you cut and paste the inputs. Okay. This one has to go there because that's where it fits. And that one has to go there because that's where it fits. Can this be hauled down one more tile? I think I've tried this before. No, it can't. All right. Now, this isn't actually where these go. You have to go down farther than that. Don't remember what this one was. These are general purpose registers. Move these boxes up. I need to think about how I want to hook all these up. There's no real reason to read select the registers. We can just turn read on at all times. And then we read select through the mux. Also, that's a lot of wires. Those all get tied together. Like so. And each of these gets tied to the output of one register. We do need to have some amount of read select though, because some things do need to be reselected, like the level inputs. Some things can't be reselected. Basically, the level input must be read selected. We do need to have read selecting for it at minimum. And how are we going to do that? We could special case it and turn all of these on. Or we could just bite the bullet and do a read selector as a standard thing. Okay, so this is register 0, which means it goes to here. Register 1, which means it goes to there. Register 2. Yeah, this is dreadfully inconvenient the way this is rigged up. How about I run this out, turn it around, and bring it back? A lot of wires, though. Um... Go ahead and flatten this out a little bit. Faster due to its way. Then what we're going to do is we are going to turn the corner and bring it back across. Because if we don't, it's going to be extremely annoying. And I just realized this is not going to help me in any way. Oh, maybe it will. I still... Damn it. I actually want these, I think. Because I'd like to do that. Upon further consideration. This gets me pin 0 right here. Or pin 1 right here, I mean. Or pin 0, pin 1, whatever, same diff. We can just run these pins like this. Instead of the way I was going to. Okay, this is the flags register. We're not going to wire the flags register up just yet. Okay, that's the select for the flag. Okay, that runs off that way somewhere. That runs off that way somewhere. There's a lot of pins. I may have placed things a little too close. Nope, we'll be fine. I really need to put register names on these somewhere. Okay, this is bank. Then here's the GP registers. Which have not gotten much press yet, but will come very much in handy when time comes to actually start writing code. All right. Now. Flags will come in from something, somewhere, someday. This is the right mux. That is not the right pin. The pin beside it is the right pin. Who the hell knows where flags is going? Okay. Like, bank is going to get a special... It's going to go somewhere to go talk to a memory controller. Whenever I get around to making one of those. I really should add a 16-bit address bus to this, because that vastly increases usability of a computer. But future Milo problems, perhaps. Yeah, the flags register stuff is probably just going to go right out across all this mess and go out here somewhere and go play it by themselves. Okay, so read select. I should probably do read select. How did you read select in the old one? I didn't hardwire them to always be on, did I? No, I did not. I just ORed together the read selects from those two. Okay. I did actually have proper read select of a sorts. Read select. Yeah, we just checked what registers were asked for and set the read select based on that. Which makes sense. We need read select for the level output. If we have to do read select for one, we might as well do read select for everybody. So there we go. Read select line right there. Now put an 8-bit OR there. There was some reason why this didn't work. No, this should be right. If we OR here, let's get the bus down to where it goes. It's a fairly substantial block of hardware. That probably is not going to go much lower than that without shenanigans ensuing. So if we ore ARG1 and ARG2 together, it's got to be more complicated than that, though. Okay. This way, if the constant is high, then we don't do this mess. Actually, we should not be using switches. We should be using muxes here. Because... No, not muxes. No, it should be switches. Because we don't have something that works the way what I want to would work. We'll put a little extra bit of logic in here. Except I need to make some more space in there so we can add some knots. Like so. And then this, I really need a documentation block to be a little closer. No. Okay. Boom. Okay. This is ARG1, and this is ARG1. ARG1 select right here. And so this goes to there, ARG1 value. And this goes to there, ARG2 value. Now this will come in right along here and go all the way down the whole line. Because this is result value, which is coming in to be stored. Somewhere. Where it will be stored, no one knows. Okay, this is load select, which multiple things can be load selected at once. That is normal. This cannot be load selected. Who the hell knows what flags is going to be doing. Yeah, that can't be load selected. It's just always load selected. Speaking of which, you are PC. Right here. So this gets run all the way out here to PC. I'm going to go ahead and label it. Because why not? I also label this one here too. Okay. I'm forgetting to hook something very important up here. Well, that is definitely a future Milo problem. And a somewhat annoying, complicated one at that. We need to use this basic system that we use for the decoders here for the mux as well. Okay, and bank. Do I have bank on the bus? Not yet. Eventually, bank is probably actually going to have to be wired high. Matter of fact, let's just do that right now. This bank is used by the memory system. So that's just wired high at all times. In the same way, flags is not used for load select either. Okay. There's I/O. And the first of the general purpose registers. Right on like that. That should be load select for everybody. Even though really only one of them actually needs to be wired. And that is the I/O. Okay. Also, PC needs to be load selected with an OR. Because we're going to be running another wire in eventually from the jump instructions to load select that, I think. Or not load select, but save select. Yes, because it's conditional whether or not we actually want to save select it. So we don't want to hard code that into the instructions that it writes to PC. The port accumulator is basically going to be turned on at all times. Anytime something else isn't turned on, the accumulator is going to be turned on. I probably should hard code everything. But instead of trying to turn on the accumulator when they don't have a valid thing to point at, they try to turn on something that can't be turned on for load select, like PC maybe. Problem is that would be a very bad idea for save select. Actually, this is kind of a bad idea for save select anyway. Oh, I kind of need a invalid save select one. Problem is, everybody uses save select. I'm gonna have to go hard code all of them to be like 255 or something if they don't actually use. Because 255 is not a valid register, and that won't be an error. It just won't turn on the save select. Probably go fix that right now. Okay, so any instruction that does not actually save to A needs to have its result, this over here, set to 255. So load parameter into A, that sets to A. Load immediate to A. This whole block is setting to A. This one, however, isn't. I should have made this the default from the beginning. Oops. Okay, LDM. Load a value from memory into A. Okay, that should be 0. STM. Store a value in A to memory. That does not write to A. Okay. LDMI. Load memory indirect. That loads to A. LDMK. That loads. STMI does not. STMK does not. And the blank instructions out here also should not store select A. Just in case anybody uses a no-op. Alright. That one's done. LDD. Load dstack to A. Implicit. LDDF. Load dstack indirect through frame. Store D. Store dstack from A. Do not overwrite A. Store D frame. Once again, do not overwrite A. Getting all these entered into the in-game editor. Okay, push. Pushes the value from A onto the D stack. Do not overwrite A when you're done. Pop does overwrite A. Actually, it may not overwrite A. It's setting to something specific. Push. Push A, or push some register. Do not overwrite A. Pop. Pops it to who knows where. Okay. Do not overwrite the A register for any of the remaining undefined instructions. Okay, jump is actually defined as writing to register 4, which I do believe is program counter. That's an unconditional jump, so it just, we're writing to the program counter, boys. Let's go. Okay, CMP doesn't write to anywhere. As a matter of fact, we could probably implement this by just injecting the opcode for subtract. Jump if 0. We don't want to overwrite anything in particular. We will be handling that some other way. Jump if not 0. Once again, don't overwrite. Don't clobber any registers. Actually, let's go ahead and tell these that they're allowed to write to 4. And then we will write, if they don't jump, they will write the next result, like where it should go if it was going to increment. So they will always write, and they will either write to... that'll save us from having to do what we did, where we added that hack. Had a special line to tell it where to go. I'll go remove that next, so you'll see what I mean. Oops. Okay, add overwrites the A register. Sub overwrites the A register. Mul overwrites the A register. Div overwrites the A register. Mod overwrites the A register. And then the remainder of these are blank instructions and therefore should not overwrite anything. Now for the last bank. And overwrites the A register, or overwrites the A register, not overwrites the A register. XOR overwrites the A register. Shift left, shift right. Okay. I should make another pass and tell them not to energize load for red for unused as well. That would require figuring out which parameters are unused and doing this exact same procedure for them. I don't feel like it. I should, but I won't. Okay. So the 0 instruction is still load A to A, basically. Let's change the first instruction here to load parameter is immediate value int A, so LDI, which would be OX01. And then boom. Short circuit. Two, 3, and 0, 1. Don't like that. Okay, who's wired wrong? That makes no sense. None of those should be energized. Okay. Q3 is activated. It definitely shouldn't be. Okay. It's receiving 1 and 255 on its inputs. Who's active? No one's active. So why are these on then? We've got a wire cross somewhere is the problem, I think. Oh, yep, right here. Okay. Is this even hooked up right? Okay, first of all, those don't hook to there. Why are these blue wires? None of these are supposed to be blue wires. These are supposed to be 8-bit. Oh. I see. Some wires got crossed, literally. And they all turned into blue wires. Okay, there's nothing connected to this anymore. Can you please turn the whole damn thing into 8-bit wire now? What happens if I exit and re-enter? Because I definitely had those all drawn out in the orange wire. And they magically converted themselves to blue 8-bit wire. Which is not okay. Let's go ahead and connect an on signal to this and see if that changes anything. Huh. I didn't know you could do that. You can hook it up and it'll magically convert itself. Like it'll magically display a 1 instead of what it's supposed to be doing. That's wild. Alright, well let's hope the rest of them didn't get somehow cross-wired like this. Because if they did, we're going to have an interesting time redoing all this bullshit. Doing it for one of them is tedious enough. This is why I'm not using colored wires. Part of it is because I like the color difference to visually tell me at a glance exactly what kind of wire I'm dealing with. I mean, sure, there's more subtle hints as to what type it is. Damn it. Yeah. Come on. I'm guessing that because none of the rest of them acted up, it's probably okay for them. Go ahead and delete that on signal. Okay, no errors. Okay. And this is not correct. It's kind of correct. It's not correct. Let's see, which wire is this? ARG2? Yeah, ARG2 is set to 255. That isn't right. It should be ARG1 that's set to 255. Okay, did I wire LDI incorrectly? If I wired LDI incorrectly, I probably wired a whole bunch of shit incorrectly. Okay, for some reason it has LDA. Oh, it's got LDA energized because that's what it's inputting. Okay. So we want upcode 1. That'll energize LDI. No, it won't. That's the bank select part. We want opcode 16, which is LDA. Or LDI, I mean. The LDI is energized. Now. arg1 select. arg1 constant is lit. Okay, something external got miswired. arg1 select. arg1 constant is not lit. arg2 constant is lit, which means this is wired wrong. Okay. Putting a 1 here. Oh, I'm not pulling in the instruction. I think I am I? Yeah, I'm not pulling in the instruction. I think I am. I'm asking for instruction 1. Who the hell knows what instruction 1 is? That'd be the first one in group 4. Would that be jump? Copy A to program counter? No. Maybe? I don't know. Whatever it is, not the right one. Don't know what instruction this is. It's writing a constant 255 to argument 2, whatever it is. It probably is jump, actually. Except it's not requesting to overwrite. No. No. We're not asking for bank 4. We're asking for bank 2. That means... Okay, instruction 1. It's actually energizing LDM. Load from memory. Load address 255. Okay. And address is stored in argument 2 for some reason, instead of argument 1. Don't know why. It just is. Or because I wrote it that way. Yeah. This should be done differently. Let's actually fix that right now while we're here. This is 255. This should not be a constant. Okay, let's see, what's LDM? Load a value from memory into A. Parameter is the address. However, that usually implies that it's pulling the parameter from a register. Okay, LDMI is basically that, but it's using... I should reverse the operands on this. Because it doesn't matter which order the operands come in, except it matters to me. Okay. And the reason it matters to me is because this way it's in the same operand order for every case. All right. We were asking for LDMI instead of, or LDM instead of what we actually wanted, which was instruction 16. LDI. Let's fix a few other problems in here while we're at it. Load parameter into A. Okay. We don't need to energize A for reading. So this should be 255. Load immediate. We definitely don't need to energize A for reading. Store A. We do need to energize A for reading, but not twice. Okay. Oops. These blank ones all get 255s. Okay. Memory loading. We fixed all that up already. Okay. Bank 1 is now fully compliant. And it is reporting a short circuit between 8-bit switch and a 4-bit mux. Because the 4-bit mux is not appropriately energized. Or rather, it's not appropriately disabled. Okay, we'll have to fix that. Next. Okay, unfortunately for me, the mux is backwards from how the decoder was made. Pin 1 is on the bottom. Which is also unfortunate for me. How could I possibly have designed this in a way that is optimally annoying? Exhibit 1. Put all the pins on in exactly the opposite direction from how I'm going to actually want them. Okay. And the other pins... then get fed into this monstrosity. To verify that they're all blank. Because if they are not, then it's not a register now, is it? And we shouldn't do anything. Okay, so these... have to be moved down. Together with the rest of this ginormous block. Okay. This is arg1 select, arg2 select, get copied into here, which conveniently we are grabbing from right over here as well. That is arg2 select. Because why would I ever make it easy for myself? Okay, let's fix this. Boom. 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 And boom. Let's do this in a sane order. Okay, wait a second. Before I get too involved, where are these going? This one is arg1. Arg1, okay. Ah, shit, we need to do this whole mess all over again. We'll fix this up later. Congratulations, you get to run around the corner like this. And one gets hooked up like so. Okay. Now... These get not gates on them, I think. Wait a second. This is backwards. These shouldn't have not gates on them. Because these are turned on if it's a constant. If it's a constant, then it doesn't get fed into the register. So these get not gates on them. The ones that had not gates on them don't get not gates on them. Okay. And that gets a disable signal. Both of them do. Because they shouldn't be outputting anything. However, they are outputting something. Alright, 4-bit mux, are you ignoring my disable signal? Yes, you are, because the output is not actually disabled. Okay, where's the disable signal? Way the hell over there. Why is it 8-bit? Two-bit mux, please tell me I didn't use an 8-bit signal for that. No, I didn't. Okay, why is it 8-bit then? Did it get its wires crossed again? Okay. Let's check the 2-bit mux, make sure it doesn't have the same bug. It does. Oh, how surprised. Okay. There we go. Are they properly disabled now? No. Why not? Because this needs to be inverted. Oops. We want it to be enabled most of the time and disabled some of the time. And I probably made the same mistake in 2-bit mux. I absolutely did. There we go. It's enabled most of the time, disabled when the disable signal is activated. Go, fix that little bug. Our previous 2-bit muxes wouldn't fit, so it deleted a bunch of them. Now it's restored them, so we're all good. Alright, we don't even need to actually hook this up to that. You just let it happily send its value into oblivion. Okay. Is it outputting? No, it's not. This one is, though, because it's not disabled. Okay. Now, we need to delete these ores. And then probably replace them with more 3-bit ores. Because we need to take these values and pass them through. So if we're calling for a constant, we don't want this stuff mucking around in our... Let's delete this. Vestiges of oldness. Now let's move everything down again. Make a little bit more room. 1, 2. Be enough. Okay, actually, do we actually have to do this? Because if this is switched off, then yes, it'll still send stuff through. Same way here. If we're getting a constant in, it'll still output. So this disable needs to be wired. Oh, it needs more than a 3-bit ore. Yeah, 3-bit ore will be fine. Wait, that's a bad idea. We'll do a simple pair of double ores. We'll put one there. Put one there. We don't want to do it that way. We need an and here, actually. If both of these are set to constants, then we don't want to write, and we don't want to read enable anybody. This is read enable, right? Yes. This one's write enable. Okay. We could totally have done a 3-bit ore here, probably. Right. Fewer gates for the wind. Okay. Now. Let's chamfer that corner too, because it looks cool. We need to do the same thing up here. Except on an individual basis. We don't need the and. Okay. That's a disable signal. And that's a disable signal. So this is held high. We want a constant on that path. The constant's already being provided. So we want these to be firmly disabled. Because constants are coming in from down here. This is where we're doing the copy over. Okay, except for the flags register, which doesn't exist. Oh yeah, I was just saying I could remove this hack earlier, couldn't I? Okay. And that hack we just removed on PC. This should be the completed register block. Bank, which is this one that is bumped outward slightly, is still not connected to anything. That's because we haven't done the memory yet. But eventually that gets connected to the memory system. Probably not going to do banked memory just yet, but it's available for when I do. I need to go in and correct some of the other instructions probably. Now we need to start doing the actual logic units. Implementing the instructions one section at a time. Basically, these 2 bits down here, they need to be re-implemented up there. We've done most of this bit. We're just missing the RAM section yet. But anyway, it's 10:30. Almost. 10:26, close enough. So I think I'm going to try to pretend that I am a responsible adult. And I'm going to call it here. And we can continue working on this lovely, wonderful, amazing game that I love a very great much next weekend. And we'll see if we can get this architecture completed and working. Because that is going to take, well, a lot of work. Oh, let's see, who's doing what tonight? It looks like our choices are Wasted is playing RimWorld, and that is it. Oh wow, Wasted's playing RimWorld with a face cam. That's not something you see very often. Okay. If you want to see what the Angry Brit looks like, let's go ahead and raid Wasted. He appears to be wearing a silly hat, too. Okay, what in the world is going on over there? Tomorrow is Monday, which means I need to go back to work. Probably crab tomorrow. Try out the patch and see how things are. There was a few nice things in there, if I remember correctly, reading the patch notes. So I'll take that for a spin. But until then, I hope you all have fun over at Wasted's, and I will see you all later. Good night, and goodbye.